Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based, of course. And as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Okay, step on inside, and given the time of year, I guess, that you're watching it right here, for me when I'm recording it, it is the end of the fall semester for my students in the Integrated Math 3 realm. A lot of Algebra 2 based material, but this is their fall final exam review. Now, I made one last year. And in the one last year, I haven't actually looked at the assignment again, but I remember it only being about 50 or so questions. In the video itself being like 3 hours. So it was something where, and I would have used it again this year, but we covered a few more topics this year that maybe hopefully, you know, some of your classes, if you're not with me, some of your classes may have covered as well. I'm going to kind of jump through the ones that I have this year, which is a lot more. I think it's over 100. I haven't actually even looked at it myself. I didn't make this one. It was one of my other colleagues, highly esteemed colleagues, who made this one. And I'll go through and try and find the ones where I'll say, if you want to find more of the same stuff, you can find it in that other video. Because I know what we covered last year in the fall, and then I know what's new for this year. And just kind of saying like I'm going to attach the other video down below. I'll give a link down below that has its own PDF. I'll put a PDF for this one as well. And eventually I'll create timestamps for this video as well. That it would take a while if it's over 100 questions, but we'll do that. And the only thing I did was I once skimmed through this to say, okay, this was all the stuff that we covered. I have no idea what else is on it, but I don't know how much room is on it for you as well. But print out what you can, use binder paper, follow along, pause when you think you need to. Eventually jump down to the description section to find all the timestamps for all the different questions, or move on from there. You know, I'm going to pop up what this thing looks like right now. I'm going to scroll through them and kind of even tell myself what order we're doing things. And I'll let you know, if there are over 100 questions, guys, and if I did 50 questions for 3 hours, I'm not going to spend 6 hours making this video. I'll see, you know, this because I've made all these things in other videos, I kind of probably just have to do the problems. Maybe the first problem I talk a little bit more on it. Outside of that, I kind of just say, here's what it is. Be careful to not do that. All that kind of stuff. So, okay. Simplify each expression. Subtracting, if you did adding, they'd be kind of the same thing there. Find each product. Distribute, that's all going to be in the previous video. Expand special cases, yeah. This binomial expansion, this is new. So you will not find this in the other video here. Binomial expansion is new. Division, longer synthetic. I assume I'd use synthetic for that one. I did that last year. Division, factor, yes. So those are the same. Factor, it says factor, it doesn't say solve. I don't mind solving that as well, unless I do solving later. Factor, find all the roots. One root's been given. I think we did something similar-esque, or we at least determined whether something was a factor. Was evaluate each function. Okay, so this will be a long video. This is new for this year, making questions like this one here, and I'll need room for this. So each time I'm going to be blanking out my problems like that just to add in space, and then I got to probably write the answer and then delete the work. So you got to rewind to it. Factor still, a lot of drill and kill on factoring. This is all unit 1, by the way, the first unit that we did that you're looking at right there. And then find all roots, that is actually solving right there. So those are the only ones we're actually solving. I guess I'll solve some of the other ones before that as well, especially if we're just factoring. It says equal to 0, so we might as well. Find the general shape. This started the next unit right here. Sketch the general shape, excuse me. Okay. I don't know if they want the intercepts as well, but I'll do as much as I feel I should. You know what, they say general shape. I don't know what I'm going to do yet. We're going to run into them when we run into them. Stated number of turns, still graphing, that's our next unit. Function operations, evaluate each function. This is new. I believe I had some questions where I composed some functions here and there, but these function operations are new for this year. So you won't find that in the old video. You won't find this in the old video here. State if they're inverses. We did inverses last year as well. Find the inverse, graph the function. Boy, this is going to be a long video. Okay. Simplify radicals and simplify through adding, subtracting. This is new. Simplifying radicals in general is something we've done, but maybe not with variables of this sort. And I know that I create my own kinds of problems that look like this, so they can get a little rambunctious. These aren't them. So we'll see. So this stuff here is new for this year. With variables as well. Okay, I didn't do them with variables with my students. And doing conjugates, that's all new. This is all new. Right in radical form, I guess this was from last year as well. You know, I don't think they were in the final review video. I think I remember that we covered them outside of the review packet, and there was another video outside of that. So this will not be found in the final review video either. There are other videos of it that I point to and refer to in that video, but they're not in that one. And okay, this is more like those, I didn't do them this year, so I'm running through just what's here. I don't do problems like this, but I will do them right here. Solve each equation, solve radicals. Again, this was not in the review video, but I pointed to another video that had these because we covered them outside of when we were reviewing for it. Solve each equation. You know, I haven't seen rational equations yet. I wonder where those will show up. Solve each equation is new. This is new. Domain range, sketch the graph. Graphing cube roots, we did that last year. Square roots, we did that last year as well, so that's not new. Here are some rational functions right here. Graph each function, rational function, identify the holes. Okay, so this stuff I started covering the second semester. I started to cover these in the second semester, and so this will be new for the final review stuff. This will be a long video. And this is old, as in this will be in that video, I'm sure. Simplify and state, multiply, subtract, add, and solve. And that's it. I say that's it. This was 142 questions. I said just over 100. No. It's 100 and a half. 142 questions. Okay, I'm going to get started. This will be a very long video here. If 142, that's 2 hours, 22 minutes. Even if I did a minute a question, 2 hours, 22 minutes. So expect over 3 hours easily for this one. You already know the timestamp is already made by the time it's uploaded. Let's go ahead and get started. Now my calculator, just in case I got to use it, I'm probably going to use it when I'm finding zeros for rational root theorem, which is also something within the factoring and solving stuff that I didn't run into. All right, here we go. Starting off, simplify each expression. So I have a negative to distribute right here. And again, I'm going to go fast as I can for some of these problems here as long as I write out the work. Distribute that negative minus 2x minus 1 plus x squared. Now, you want to write this in standard form as well. So I'm going to combine my x squareds first. 5x squared plus 1x squared is 6x squared. Negative 4x minus 2x is negative 6x. And 1 minus 1 is 0. So it's just 6x squared minus 6x. I'm good. Moving on. Number 2. Again, distributing the negative. If this was a plus, I'd just be distributing the positive. If there was another number, I'd be distributing that value. All that good jazz. I got 5v cubed minus 5v minus 4v to the fourth minus 6v cubed minus 2v to the fourth. The only thing, oh, they all combine, sort of. Negative 4v to the fourth minus 2v to the fourth is negative 6v to the fourth. I have 5v cubed minus 6v cubed, which is negative 1v cubed. I have a constant and it's linear, so negative 5v minus 2. Right there. That looks like standard form. That looks like it's all combined. Let me know if I already made a mistake early on. I may have. All right, these problems should go a little bit faster here. Find each product. It's distribution of 8 times 6x and 8 times negative 4. That's 48x minus 32. Nothing will combine there. They shouldn't if they didn't early on. Same thing here. 8 times and 8 times there. There's not much happening on these problems here. 64n minus, once again, 32. Okay. This is going to use the FOIL method, multiply each term in one quantity by the other terms in the other quantity here. So 7k times 6k and times 3 gives us 42k squared plus 21k. And then negative 5 multiplies with 6k and 3. So negative 5 times 6k is negative 30k. And negative 5 times 3 is negative 15. And I am going to be going faster on problems like this over time, especially when we have to FOIL things with the radicals and such. I'm going to do a lot of it mentally. I'll say it out loud, but I'm going to do this a lot faster after a couple times through. So 42k squared is the first term in standard form. 21k minus 30k is negative 9k, and negative 15 rounds it out. It's a trinomial, quadratic trinomial. Same thing here, 7k times 5k will give me 35k squared. Then I have plus 21k, and then once again a negative 5 multiplying, so negative 25k here, and then negative 5 times 3 is negative 15. And that'll give me 35k squared minus 4k minus 15. Okay, now it's not FOIL anymore. I have to multiply 2 by 3. So 2x multiplies with 3x squared, negative 7x, and negative 5. 6 will multiply 3x squared, negative 7x, and negative 5, and combine what we can. And I'm going to be writing it as one string. I'm just going to fit within this picture here, but maybe on this problem I'll do my little 2x3 diagram just to show you another version of. So first time through, let's check it out. I got 6x cubed, and then negative 14x squared, and then negative 10x, plus 18x squared minus 42x minus 30. Now this combines to 6x cubed minus 14x squared plus 18x squared is 4x squared minus 10x minus 4 minus 52x and then minus 30. Now this next problem I'll do the same thing. I will show a 2x3 grid this time if you prefer this once the values get a lot bigger here. I can multiply 2n plus 8 with 3n squared minus 7n minus 3. 2n times 3n squared is 6n cubed, kind of like the last one. 8 times 3n squared is 24n squared. 2n times negative 7n is negative 14n squared. 8 times negative 7n is negative 56n. That's an n. 2n times negative 3 is negative 6n. And 8 times negative 3 is negative 24. Oh, 8 times negative 3 is not negative 6n. I don't know why I said that. 2n times negative 3. That's correct. Okay. So this will become 6n cubed. Let's do this in darker green. 6n cubed. Negative 24n squared minus 14n squared is 10n squared. Negative 56n minus 6n is negative 62n. And then I have negative 24. So there's another alternative you can kind of use like that. Diagram it up. That works. All right, 6x squared minus 6 quantity squared. It is not 6x squared minus 6 squared or anything of that nature. No. It's a perfect square trinomial. It is 6x minus 6 times 6x minus 6, of course, like that. I have a lot of ways. I would have probably factored out these 6's if I'm going to go about it that way. And you can FOIL that guy, and that gets you 36x squared minus 36x minus 36x plus 36. I'm just making sure I did that right because I'm seeing the 36's. Of course, that's going to happen. And that becomes 36x squared minus 72x plus 36. Every so often, my students will go like, and then I factor it into, no. This is the factorization. I mean, there's a 6 GCF or a 36 GCF, if you will. But no, don't factor it. That was the whole point. We are expanding. It is done. Now, that's not generally how I will do these problems that are squared. I'm showing you one version of why it is not just the two terms, a squared minus b squared, or a squared plus b squared. There are more terms there. Now, this time I'm going to use the actual form that a plus b quantity squared is a squared plus 2ab plus b squared, just in one fell swoop. Let's just do it like that. That's a squared plus 2ab plus b squared, which is 9k squared plus 6k plus 1. And of course, one of those things that I tend to do mentally more so than even write that out. But there's a middle term that cannot be missed or ignored or avoided. Difference of two squares. I'm going to jump straight into it right now. The middle terms will cancel. This becomes a squared minus b squared because 64x minus 64x cancel. And then the first and last terms are opposite signs of each other. This becomes 8x squared minus 8 squared, which is 64x squared minus 64. And done. Same thing here. Again, I wish some of the problems changed what they were doing instead of 8's again. But again, it's a squared minus b squared. This becomes 4x quantity squared is 16x squared. And then minus 8 squared is minus 64 on number 12. Same thing, difference of two squares. Middle terms cancel out. 1 sign changes in both binomials. Okay, expand completely. This, and again, I'm not going to get deep into the why of the matter. However, you could, if you expanded this, you could do 2y plus 1 times 2y plus 1 times 2y plus 1. And if you do so, you don't just multiply these. You don't just do 2y times 2y times 2y and then like 1 times 1 times 1 or anything like that. You would have to multiply bits at a time, those two, and then multiply it with that one that multiplies. My students get this wrong all the time because they start adding things instead of multiplying them. I'm not going to do it that way. We're going to use Pascal's triangle, see if we can make sense of it from that. This is, if you haven't learned it before, I'm not going to explain it too much here. I'm going to show you the process of which you can make it work yourself. In building this triangle right here, there are several rows of these values here. They multiply. They're scalar multipliers by how many times those variables of those degrees are adding with each other when you combine all like terms in your polynomial after expansion. And the degree is based on the row we're talking about. This is called row 0, row 1, row 2, row 3, row 4. This is built by adding up. 1 plus 1 is 2, 1 plus 2 is 3, 3 plus 3 is 6, etc. You can keep building this infinitely, but I only need row 3 and row 4 for this one. Row 3, degree 3 binomial expanded has 4 terms in it. The first term will multiply this 1 by the first term raised to the third power and the second term raised to the 0 power. And then the second term will multiply 3 with the first term raised to the second power and the first term raised to the second term raised to the first power, plus another 3 times the first term raised to the first power and the second term is squared, plus 1 times the first term raised to the 0 power and the second term is cubed. Now, 1 times, anything to 0 is 1. So 1 times 1 is 1 times 2y quantity cubed, that's 8y cubed. 2y quantity squared is 4y squared times 1. These ones aren't really going to change anything, right? Times 1 is 4y squared times 3 is 12y squared. 3 times 2y is 6y, and then 1 times 1 times 1 is 1. And there's your binomial expansion, the power of 3. This next one's going to do the same thing. I'm going to use the fourth row 4 I should say. This is row 0, 1, 2, 3, and 4. It's going to have 5 terms in it. This one, you can kind of see what happens in the first and last terms. It's going to multiply 1 and 1 with something to the 0 power, which is 1, and something to the 0 power, which is 1. It's just the other terms raised to just that number. So in the first set right here, I'm going to have, I don't really know where to fit this because the triangle pyramid's in the way. Let me kind of move it down. I think you know the numbers, right? 1, 4, 6, 4, 1. I can't seem to drag this after. There we go. 1, 4, 6, 4, 1. I know them at least. All right, so 1 times x to the 4th times negative 4y to the 0. That will be 1. I'm just going to leave that like that. Plus 4 times x cubed times negative 4y to the first power. That'll just be negative 4y. Plus 6 times x squared times negative 4y quantity squared. You notice how the first terms go down in degree, the last terms go up in degree. Plus 4 times x to the first power times negative 4y cubed, plus 1 times x to the 0, which is 1, times negative 4y to the 4th. This will equal x to the 4th. Now, negative 4y, the negative will give us a minus here. 4 times 4 is 16, and I have x cubed y. Plus, and I say plus because negative 4 is about to be squared. That'll give you positive. 16 times 6 is 96. So 96x squared y squared. And then minus, all the signs will alternate here when this negative is raised to an odd power versus an even power. 4 cubed is 64, times 4 is 256. So 256, that's xy cubed. And then plus 4 to the 4th, again, is 256. And that's y to the 4th. X to the 0, y to the 4th right there. And there is our expansion. Okay, there it is. Okay, state if the, they do have these questions. State if the given binomial is a factor of the given polynomial. You could do it basically through division. If you divide this thing and the result doesn't have a remainder, then it means it's a factor. That's it. So if we use synthetic division on this, we can do exactly that. Now in synthetic division, we use the root of this factor. If v minus 4 is 0, then v equals 4. 4 is a root. I will represent the coefficients in descending order of degree in standard form. 1, negative 12, 35, negative 2, negative 33, and negative 26. And I'm going to attempt synthetic division on this. Bring this 1 down, multiply it by 4, add it with negative 12, multiply it by 4, add it with 35, multiply by 4. I'm telling you the process out loud so you realize what's going on there. And we get 2. Now this ends up being as a, when I divided this, v to the 5th, divided by v minus 4, this became 1v to the 4th minus 8v cubed plus 3v squared. I'm not going to write the whole thing, so we'll do division later. This is the constant. It's plus 7. I guess I'll write it. plus 10v plus 7. And there's a remainder of 2. This is plus 2 over v minus 4. There's a remainder of 2. It's not 0. Unless I did math incorrectly, which I may have. I don't know. We're going to multiply by 4 anyway. It's not going to add up 26. With that remainder not of 0, that means that no, v minus 4 was not a factor. It doesn't factor wholly into it with the remainder of 0. Okay, so that was the show. That was the show of that. No. Number 16, let's do the same thing on this one. This is n minus 6. That gives us 6 as a root. So 1 n to the 4th minus 13n cubed plus 36n squared plus 34n plus 12. By the way, if there were any missing terms, if there was missing an n squared there, it just said minus 13n cubed plus 34n, I'd put a 0 right there. You need a placeholder value right there, but it's there. All right, bring the 1 down, multiply by 6, add that, multiply by 6. Let's hope this one works, just because like we want one that works and one that doesn't, so you know what it looks like for one to work and one to not, and what it actually means. So this has that remainder of 0 right there. This has remainder of 0, therefore yes, that one is. And I could have used long division, but I won't use it unless I need to, which is like if I'm dividing by a quadratic or something like that, or if I'm doing, maybe when I do, when I divide by quadratics, maybe when I do those complex rational functions eventually. All right, divide here. It's more of the same, and I'm going to use synthetic here with the little room that I have. I guess I could do it down below, unless I can fit it. Let's try it. 4 is a root. 4 is a root. I got 1n cubed minus 12n squared plus 37n minus 22. Yeah, I can fit this. All right, check out the speed here. Okay. So now this isn't asking if it's a factor or not. It is asking us to divide and write the result of it. So this divided by this equals 1n squared. We go down a degree when we use synthetic division, dividing by a linear factor. 1n squared minus 8n plus 5 with a remainder of 2, or negative 2. So it's minus 2 over n minus 4. That is also to say that this times this equals that. All right, that's what that means. But anyway, this is the division and the result of that. All right, going down in standard form right there, same-ish. So here we go. We have a root of x plus 5 is 0. That'd be negative 5 as the root. And this is 1x to the 4th plus 8x cubed plus 21x squared, 26x minus 24. I do like synthetic division quite a bit. Given that it works, you know why it works, or given that you know why it works, and that you trust the process. I don't like things that are shortcuts for working just because, without having any actual merit. This one has very much merit to it. It's cutting through some things. It's cutting through the hoops of not needing to write variables, and it's adding instead of subtracting because it's doing some things with the root. As long as you know what you're doing with it, it's all good. All right, so this becomes 1x cubed plus 3x squared plus 6x minus 4 with a remainder of negative 4 over x plus 5, like that. And if the remainder was 0, then I just wouldn't write anything after that. It would just be the polynomial. All right, factor each completely. Now, I made a big factory video. If you want to find that, it's about 270-something problems of just me factoring, just all the time, just whatever it is. So these are going to go just as fast as that, as much as I can here. I always look for greatest common factors first, none of which seem to exist here as much as I'd love them to. And this has 4 terms here in standard form. It looks like I can factor by grouping. I can find greatest common factor of the first 2 terms to get 4x squared can come out of that. And inside I'm left with 3x. I haven't factored in in a long time. Plus 4. And then subtract, minus factor out a 3. Out there, a 3x plus 4. Now, you can't automatically factor by grouping just because there are 4 terms. If they don't factor by grouping, if this wasn't identical in both, then I'm jumping into what's called rational root theorem, which I hope we have some questions like that. And if we don't, then we have to deal. We have to figure out this video won't have it. So this factors into 4x squared minus 3 times 3x plus 4. All right, let me see how much time. So I've probably spent about a minute a problem on average so far, given that I had kind of a 5-minute intro or so. Next one right here, number 20. It looks like I can also factor by grouping again. If I factor out 7r squared from the first 2 terms, I'm left with, r squared, not 7r squared. R squared from the first 2 terms, I'm left with 7r plus 6. And I factor a negative 1 out of here, I'm left with 7r plus 6. That kind of seems to pan out. And that equals, oh boy, I'm going to need some room. Hold on. let's move those up. And this will equal r squared minus 1 times 7r plus 6. Now, I'm not done on this problem. Unlike the previous problem here, this was not a difference of two squares, because 3 is not a perfect square, even though 4x squared is. This is a difference of two squares. This factors into r minus 1 times r plus 1. One of the many reasons you want to know that a squared, a minus b times a plus b is a squared minus b squared, so you know when to factor it and what it looks like when you do. And there's the full factorization. When they say completely, we spare no expense. We leave no stone unturned when we go ahead and do that. All right, 250x cubed plus 432. I see a GCF of 2 at the very least. I believe that'll probably, actually, I don't know for sure. No, 4, yeah, 2. 2, and you get 125x cubed plus, what is that though? 216. 216. Now, you would be done if there's nothing else that you could do here, but this is a sum of two cubes. This is a cubed plus b cubed. You know, this is 5x cubed plus 6 cubed. And that I didn't factor here. I'm recognizing it for what it is, a sum of two cubes. The factorization of a sum of two cubes, a cubed plus b cubed, factors into a plus b times a squared minus a times b plus b squared. And that, folks, is the full factorization of that guy. This guy right here does have a GCF that could be 4 this time. I believe it is. Factor a 4 out of that. I'm trying to always decide 8. I don't think so. And that is 125x cubed. We just saw that. Minus 8. This is a difference of two cubes right here. That is 5x cubed minus 2 cubed. So with the 4 being on the outside there, this is 5x minus 2, a minus b, times a squared plus ab, 5x times 2 is 10x, plus b squared, 2 squared is 4. And this trinomial cannot factor further. This trinomial cannot factor further. I'm curious whether there will be normal quadratic things to factor. I hope there are, because those are ones that we spend a great deal on. I know we're going to be doing those when we start multiplying and dividing the rationals and adding, subtracting the rational expressions and equations. I'm sure we'll run into them there. I hope we run into 1 or 2 here, but this is probably more part of the IM3 stuff, not the IM2 stuff. All right, I can factor a 2 out of here, and I get x to the 4th plus 8x squared plus 16. This is a quartic in quadratic form as they descend in degree by 2s from this term to the constant. This is kind of like, you know, instead of multiplying x by x to get x squared here, I can multiply x squared by x squared to get x to the 4th. The last two terms here will multiply to the constant, and the middle two terms will combine to be x squareds. So now I got to figure out what two terms multiply to become 16 and add to become 8. Well, that's 4 and 4. You know, this is a perfect squared trinomial in disguise because it's a perfect quartic trinomial there. X squared plus 4 times x squared plus 4, which cannot factor more, but I can collapse and condense this into x squared plus 4 quantity squared. Now, is that a required right? I wouldn't say so, but given that this is a final exam review for my students, they'd have to understand it's a multiple choice test. And so you don't see this answer, you see this answer, you want to recognize what it's supposed to be. Plus, you probably want to know this condensing thing when we graph our polynomials, because that's when we start talking about multiplicities, a multiplicity of 2, for example, for this imaginary solution. I guess that doesn't count for this one. And then the last one on this page, I don't know what exists on the other side here. 5 looks like a GCF, and we're left with a to the 4th minus 6a squared minus 16, I think. And that equals 5 times, it's another a squared business, a squared, negative 8 and positive 2. Negative 8 times 2 is negative 16, and negative 8 plus 2 is negative 6, and there's that. If this was a difference of two squares, I would factor it down more. It is not, so I will not. And this is not, there is no sum of two squares to be talking about factoring or anything like that. We are finished on that one. I wanted to mention something, I forget what. Oh, yes. These are not set equal to 0 either. This doesn't say equals 0 equals 0. We're not using zero product property in solving this. We are factoring the expression only. There is nothing to solve. That's something I yell at my students at over and over. Not literally yelling, but I'll yell on paper. I'll capitalize the words. I'm like, we're not solving. What are you doing? Okay, more of these. They do show up some more. And with GCFs. I mean, you know what? I love the GCF talk because you always look for GCFs. The question is, what is the GCF here? And I can see that 4 might be it. I'm going to pretend like it's 4 and see if that works out first. 5x to the 4th minus 44? Yeah? No. 34. No. Darn it. I can't do this. 39. 39x squared minus 54. Can anything else factor? No, any other GCF? Okay. Okay, let's go with that. I hope I did that correctly. Now, this is going to be some sort of 5x squared times x squared right here, because 5 being a prime number means that's what's left. One will be a plus, one will be a minus. I'm not sure which. I imagine this will be the minus because we're going to get largely negative here. Multiply by 9, I think it's this. 9 and 6. Negative 45 plus 6 is negative 39. 6 times negative 9 is negative 54. That seems to work out. So this will equal, this is a difference of 2 squares right here. And this will be x minus 3 times x plus 3. And we are done. I liked that problem the most so far out of the factoring because of what you have to explore in it. I like to be myself. All right, there's no GCF on this one, so I'm just going to jump straight into it here. I got some 7x squared times x squared coming about. I will have a minus and a minus here to get the positive product and negative sum, and it's got to have a 4 and a 1 somewhere. I imagine we're going to multiply the 7 by the 1 and the 1 by the 4. The 1x squared by the 4 to get negative 11. Negative 7 minus 4 is negative 11. Okay, this is a difference of 2 squares, x squared minus 1. So this gets us 7x squared minus 4 times x minus 1 times x plus 1. If you haven't seen the factoring factory video, I do this kind of stuff 278 times or something like that. It's the wicked number. Okay, 2 more on the factoring. Well, not really. 2 more on this stage of kind of, I don't know. We'll see what there is. Looks like there's nothing that can factor outside of a negative 1. And you do want to factor that thing out right there. It'll give us 10m to the 4th minus 37m squared minus 36. Trust me, it saves an entire... First of all, that's part of the factoring. Factor no negative leading terms. That's a part of it. Secondly, it saves the headache of screwing up later. Trust me. Just trust me. All right, this is some sort of m squared times m squared. I don't know if it's 10 times 1 or 5 times 2. Because the numbers don't get too outlandish, I'm going to start with 5 and 2 and see where we go from there. 1's adding, 1's subtracting here. It won't be 6 and 6 or 18 and 2. I'm going to try 9 and 4 with the 36 thing. 4 and 9, no. 9 and 4, I think yes. Negative 45 plus 8 is negative 37. Yeah, I was going to explain why it won't be 6 and 6. It has to do with the fact that this is an odd coefficient, not even. That's all I'm going to say. If you've learned some of my stuff before, then you know. Oh, and that's it. That's all it factors to there. No difference of 2 squares. I am done. So there's good strategic factoring of which you can be a master at. All right. Looks like 5 is a GCF at the very least here. And that'll give me 8x to the 4th minus 2x squared minus 45 minus 45. My nose always gets itchy right when I start recording a video. I don't know why. All right. Now this one is going to be 4x squared and 2x squared, given this is an even number here, and this is only odd factors. So you're probably look at 9 and 5 to start with there, and it's got to multiply to 2. I'm going to try the 9 here, the 5 here. I imagine that's going to work itself out. We got to figure out what's negative 20 plus 18. Yeah, so negative 20 plus 18 is negative 2. Yeah, and no difference of 2 squares or anything, so I'm done. So you can get pretty good at those if you practice over and over, and it's good. Now this says factor each. I am going to go ahead and solve as well. I don't know how often we get to solve these. I imagine probably a lot. I take it back. I'm not going to solve if I have to use quadratic. Find all roots. Factor and find all roots. We have to do it later. Okay, I'll solve them. No, I won't, because these, I'm not going to solve. I'm not going to solve. Why does it say equals 0? I don't know. I'm going to leave them. I'm going to pretend like they're not there. Because I don't want to solve these ones here later, whatever. All right, let's just keep factoring. Let's keep doing what we were doing. 3x squared. Should I solve them? I'm going to solve these two and change the instruction to say solve. I don't know yet. I probably should have brushed up on these beforehand. I'm at least going to put equals 0 to start with here. It does say factor. It didn't say solve. I wonder if other questions ask us to. That's all. That's the only thing I'm concerned about there. Okay. 6, 7, 7, 6, 6, 7. Yeah, 7, 6, 7. Sorry, that's my thought process. Negative 18 plus 7 is negative 11, and 7 times 6. Yes, yes, yes. If I were to solve, let me factor this one first and decide if they're both good solving ones, as far as telling you what's going on. Because I know we had to solve in this unit. All right. 42. Let's try 7 and 6 again. Negative 7 plus 6. Negative 6 plus 7. Negative 6. Negative 12 plus 7 is negative 5. All right. I'm going to go ahead and not solve. These are literally going to give us the same kinds of answers there later. I hope we get to solve later. I do. Maybe I'll go back. Gosh, do we get to solve? State the possible. All right. Let's solve these two. Okay, we're going to solve using square roots on these, though. There's not much to them after, other than this is zero product property. This times this equals 0, so either this equals 0 or this equals 0. Now, if x squared minus 6 equals 0, I can add 6 to both sides and take the square root of both sides, and I'll get plus or minus the square root of 6. And that's going to be true for this one as well, plus or minus square root of 6. That's one thing I'm noticing. However, on this one, I have to subtract 7, divide by 3, and then when I take the square root of both sides right here, I will still have a plus or minus. However, this is an imaginary solution set here. This is going to be I times the square root of 7/3, or I times square root of 7 over square root of 3. And then I must rationalize this denominator by multiplying top and bottom by root 3 here, which then gets me plus or minus I times square root of 21 all over 3, like that. That is the solution for that guy. This one will be identical, except it'll be plus or minus I root 21 over 2. Excuse me, not 21, because I'm multiplying top and bottom by root 2 over root 2. So plus or minus root 14 over 2. I root 14 over 2 right there. So that's for this one here. That's as deep as I'm going to get right now, just to show you that they are there. I don't think I'm going to solve these. They get a little large and in charge. It depends on what the numbers are. Now, factor each one root has been given. These could be like rational root theorem kinds of problems, but they do give us a rational root. So I'm going to use this to break it down. Now, they say a root has been given, but at the same time, I don't know if I'd prefer using it, because I can factor this thing by grouping. Okay, I'll follow what they say. I could factor this by grouping, and that would be a good start, but you know what? They give us the root. Let's see if it leads me to good stuff. Okay, so negative 3 is a root. Let's use synthetic division given that. 2x to the 6th, 6x to the 5th. I'm sorry that I'm fighting the worksheet. Negative 15x to the 4th. Negative 45. It humanizes it more with a teacher fighting it. 20x squared plus 84x. Now here's the thing. Oh, there's another. Oh, I didn't notice it went down to 0. I couldn't factor by grouping then. I could have. There's a GCF. Oh, yes, I could have. Okay. Anyway. You know what I should have started with? The GCF. Let's do this. I didn't notice. I thought this went down to the constant. Notice how I put a 0 here? That's because this is plus 0 as the constant. You do have to go down to the constant in standard form. So let's do this. Let's factor an x out. And I think that's as much as I can factor out as a single GCF. And that gets us x times 2x to the 5th plus 6x to the fourth minus 15x cubed minus 45x squared plus 28x plus 84. And I know that doesn't sound like a lot that I just did that right there, but it does help in that I can knock this 0 out. I don't have to imagine that it should have been there, should have not, or whatever. I know that x equals 0 is one of my solutions. Obviously, I know that negative 3 is one of my solutions. But I'm going to use negative 3 in synthetic division to divide that part out because we technically already divided out the 0 root. We divided out an x from here. So let's keep going from that and work it down to a quartic and then see what we can do from there. So now we're going to get 2 here, negative 6. Okay, yeah, let's use this version. 0, negative 15, that's 45 and 0. And 0 and 28 and negative 84 and 0. As it's a root, that should give you a 0 remainder. So now our, very little room. Now our polynomial looks like x times x plus 3. That's from negative 3 being a root. X plus 3 is the factor. And then times 2x to the fourth minus 15x squared plus 28. That all equals 0 still. Yeah, I might be able to solve these pretty kindly, all depending. I don't know if this is further factorable. Let's take a look and see if it is. If it is, then that would give me 2x squared here and x squared here. 28 can be like 7 and 4. I'm always going to start with the kind of obvious ones there. So negative 4 and negative 7, that's negative 8 minus 7 is negative 15. And then that can factor to x minus 2 times x plus 2. So as a full factorization, I'm going to put the x minus 2, x plus 2 first. X minus 2, x plus 2, and 2x squared minus 7. As a full factorization, it would look like that. As a solution set, as I vowed to, I guess, kind of solve these if they factor out okay, our solutions are x equals 0, as I already mentioned, x equals negative 3, as they already mentioned, x equals 2, really plus or minus 2. X equals plus or minus 2, positive negative 2. And when 2x squared minus 7 equals 0, that means 2x squared equals 7, x squared equals 7 halves. And we just saw this before, but it had an I in front of it because it was 2x squared plus 7. This is 2x squared minus 7. So this will be plus or minus root 14 over 2. Plus or minus root 14 over 2. Did they ask us to solve? No, they didn't. I'm doing that because I don't know if they ask us to solve later. So I want to cover ones here because it could be a part of your final. I mean, hey, why not? Especially if you're not in my class. And solving by factoring uses zero product property. We haven't had to use quadratic formula yet. We could have there. I want to solve using square roots there. Okay, this one also has a GCF of x. Let's go and whittle that down just like I did before. GCF of x, and I have 6x cubed plus 13x squared minus 10x plus 1. This cannot factor by grouping, so having this 1/2 as a root is good. That being said, what do I want to say with that? That being said, we could use rational root theorem and perhaps find a better root than this, not necessarily sure which. Now, given the 1/2, you have choices here. And I'm going to whiten this out for a little bit just to talk about this. X equals 1/2 being a root. If I multiply both sides by 2, then I get 2x equals 1, right? Times 2 times 2. And I'm showing you this because whenever we write out factors, whenever we say something's a factor, we're referring to an integer set. Notice where I'm pointing to an integer set of factors right here, just like this, just like this, right? And I want factors here to say what equals 0 if I subtract 1. 2x minus 1 equals 0 means that 2x minus 1, without a GCF of sorts, is the factor which will exist in our polynomial. And I say this because if I just use 1/2 in my synthetic division, everything will still be 2 times 2 large, and then I can still divide a 2 out of them and put the 2 in here in its factorization. I might as well use this factorization early on or not use synthetic division, which means I could use long division on this one. Why don't I use long division on this one this time? I'm going to do 6x cubed plus 13x squared minus 10x plus 1 divided by 2x minus 1 like this. This will be the same thing as using synthetic division with 1/2 and then dividing everything by 2, but now I clearly know what one of my factors are and I'm not having to use a fraction along the way. Not that I think it would bother me too much. I'm sure multiplying by 1/2 is dividing by 2, and I'm sure they'd leave us with integers. Otherwise, this wouldn't be a root. All right, so 2x goes into 6x cubed, 3x squared times. Multiply those, and listen, this will probably be slower. Multiply those right there, and then we subtract. 6x cubed minus 6x cubed, 13x squared minus negative 3x squared is positive 16x squared minus 10x plus 1. If you see me do long division before, then you know I don't change the signs and I don't write subtraction. I just do it. Sorry about that. If you haven't seen me do it before, I'm sorry about that. 16x squared and then minus 8x here. Subtract. That's negative 2x. And then 2x goes to negative 2x, negative 1 times. That's negative 2x. And then plus 1. Subtract those. You get a 0 remainder as expected. And now we have this. So this is now factored into x times 2x minus 1 times 3x squared plus 8x minus 1. This all equals 0 here. You could solve, if you were asked to solve, you could use quadratic formula on this right now. I imagine it's not factorable. That's not factorable. So if I were to solve, good, I get to talk about quadratic formula. If I were to solve this thing, as it looks like I'm solving, this will become x equals 0. We already know this is x equals 1/2 right here. And this one, 3x squared plus 8x minus 1 equals 0. It's not factorable. I don't want to use completing the square, so quadratic formula is in the works. That's x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And I'm happy to do these, even though it's going to stretch out the time, because I don't know if there are other problems where we're going to be asked to do that. So it's probably good to do it here. I'm going to start with the discriminant called b squared minus 4ac. That's b squared minus 4ac, which is 64 plus 12, which is 76. 76 does, 76, when I take square root stuff, I think it can break down more. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. All right, 76 is 4 times 19. 4 times 19. So root 4 times root 19 will give me 2 root 19, and this is all divided by 6. These can all divide by 2 here, so this will be x equals negative 4 plus or minus 1 root 19 all over 3. So those are two different answers right there. So negative 4 plus root 19 over 3, negative 4 minus root 19 over 3. And those are the other answers. So x equals like that. Okay, there's probably one more thing that I at least want to mention here before moving forward, even to the next. Was there a next problem? Maybe not. Before moving on to the next set then, because otherwise this is going to erase, right? So here was the full factorization. I'm going to start right there. Here was the full factorization without minus the equals 0. That's as much as I could break it down. And then here are the solutions. Now, one other thing I want to mention, it's called the fundamental theorem of algebra. And I'll go back to all the previous problems that we've already answered here, which states this. The number of degrees of the, because I think it's going to lead to something we do with polynomials later. The number of degrees of the polynomial in the polynomial, like this degree 4, degree 6, degree 4, degree 4, also express how many solutions there are, real and imaginary. How many complex solutions there are, real and imaginary. Multiplicities included. I don't think we saw any multiplicities here, but that'll happen. So with this x to the 4th right here, there should be 4 solutions. What were they? Root 6, negative root 6, I root 21 over 3, negative I root 21 over 3. This had the 4th degree, had root 6, negative root 6, I root 14 over 2, negative I root 14 over 2. This degree 6 had 6 of them. It had 0, negative 3, 2, negative 2, 14 root 2, negative 14 root 2. Excuse me, root 14 over 2, negative root 14 over 2. And this one had 4 of them right here, which were 0, 1/2, negative 4 plus root 19 over 3, negative 4 minus root 19 over 3. And there were the answers right there. As far as me solving, right? Because I said I'd solve on those. Okay, I got to wipe all of that out except for, I guess, the solution set. I want to find a way that I can get those together, bring them up, and erase the rest. This might not be very easy to do. Okay, so moving on from those, as I've padded the runtime quite a bit here, unnecessarily so. I mean, it's not unnecessarily, but something that I don't want to do, right? This will be a long video here. I mean, I'm starting this pretty late. It's already 9 p.m. where I am right here. So, yeah, till midnight we go, yeah? All right. You know what I hope I have? You know what? I don't know if I have enough computer space for all this. Memory. Let's see. I really doubt I do. All right, factor, find all roots. One root's been given. Okay, this is more of the same. It's more of the same. -3 right here is a root, so let's start speeding this up. Talking a lot less if I'm able to. No GCFs. So 5, -5, -5, and 3. Okay, here we go. All right, you want the 0 remainder. That's going to work out. So right now this is factored into... See, oh, now it says find all roots. Oh, man. How did I not read that? All right, I solved prematurely. That's okay. I have already done it. You can't erase that. Okay, this becomes x plus 3. That's the factor from the -3 root times 2x cubed minus x squared minus 2x plus 1. This time we must solve, right? That's kind of what's being asked. Here I can factor by grouping, and I'm going to go ahead and do that. And x squared can factor out, and I get 2x minus 1. And here a -1 can factor out, and I get 2x minus 1. And you definitely want to write that -1 there, like as a part of it. Now this factors it to x plus 3. X squared minus 1 is x minus 1 times x plus 1. And there's a 2x minus 1 factor left. Your solutions, your 4 solutions, will be -3 plus or minus 1, 1 and -1. And add 1, divide by 2, you get 1/2. That's me kind of getting a little more speedy on that one. You know what I do like about doing the previous problems before was for solving, I got to talk about solving using square roots in case none of these are square roots and quadratic formula. So no regrets. Last time I used the long division here. This time I'll use synthetic division with the 1/5, noting that if x equals 1/5, then then 5x, if x equals 1/5, then 5x equals 1, therefore 5x minus 1 is a factor that's going to exist for us, which means once I use 1/5 in my synthetic division, I am then going to divide my values by 5 as well. Speaking of, is there a no. I was going to ask if there was GCF of 3 in these. Doesn't look like it at all. So 1/5 this time we're going to use as it. And you do have to use the root. You can't use like 1 as the thing or whatever, right? 1/5 is the root. So either you use synthetic or long, and it's up to you. I'm going to this time use synthetic. I used long on that previous problem about 3 problems ago. I'm going to go and use synthetic this time. All right, 30. 1/5 of that divided by 5, right, is 6. So 80 divided by 5 is 16. Add those. You get 105 divided by 5 is 21. Add those is negative, what is that, 45? Negative 45 divided by 5 is -9, and 0 right there. Now, this is if this was multiplied by x minus 1/5. But I'm turning this into 5x minus 1, so I'm going to divide all these by 5. So divided by 5, I don't know how else to put it right now. And that's going to have a 6, a 16, a 21, and a -9. So this has now become 6x cubed. I'm sorry, this is 5x minus 1 times 5x minus 1 times 6x cubed plus 16x squared plus 21x minus 9. This all equals 0. Now this does not look like you can factor by grouping. They only gave us this one root as 1/5 right here, so we have to use rational root theorem to find another root that exists in these. There is no GCF still. There hasn't been, there won't be. Now, as far as rational root theorem goes, the idea is that in this particular polynomial set, there are p's over q's which exist. Some people say m over n and things like that. When I divide factors of 9 by factors of 6, both the positives and the negatives of them, I will be able to test those and figure out what else exists as a rational root in here. There should be at least one more. There will be at least one more. So factors of 9 are 1, 3, and 9. And we're going to divide those by factors of 6, which are 1, 2, 3, and 6. So your possible solution things are plus or minus 1 plus or minus 3 plus or minus 9. We're dividing those by 1. Now let's divide them by 2. Plus or minus 1 half plus or minus 3 halves. That's 3/5. Plus or minus 3 halves. Plus or minus 9 halves. Let's divide them by 3. You divide plus or minus 1/3. You divide 3 by 3, you get 1. 9 by 3, you get 3. We already saw those ones. Now we got to divide them by 6. Plus or minus 1/6. You divide 3 by 6, you get 1 half. We already have that. You divide 9 by 6, you get 3 halves. We already have that. So these are the different 1, 2, 3, 4, 5, 6, 7, 14 different factors, possible rational roots that we could test for and see which ones exist within here to work out. Now I could try and plug in numbers manually. I will do them manually with 1 and 3 and -1 and -3. After that, I'm going to go to the calculator if none of them work. So 1's not going to work. That gives us 6 plus 16 plus 21 minus 9. That's not going to be 0. You're going to plug them in and see which ones you get 0. -1. That's -6 plus 16, which is 10, minus 21, which is -11 minus 9. That doesn't work. 3 cubed is 27 times 6. Okay, that number's going to get a little big. All right, I'm going to go to the calculator for the rest of it here. This is where, let me type it in the calculator. I'm going to pause my video, and then I'll unpause, and we'll figure out where to go from there. Okay, that actually didn't take too long. Let me pull up my graphing calculator now. Okay, so I just typed that in. So I'm going to start plugging in values here. Let's ask for our own values here. So I tried to plug in 1 in my head. That didn't get me 0. -1 didn't get me 0 in my head. Let's try 3. Nope, -3. 9, -9. So it looks like we'll have to deal with the fractions. Let's try 1 half. Can I delete? I'll just type them down here. I think they're going to be on the bottom now only. 1 half, -1 half. And the scary part is I want to make sure I did everything correctly. If I didn't, then this is going to be forever just to figure out it didn't work. 1/3, no, excuse me, 3 halves. 3 halves, -3 halves. 9 halves, -9 halves. 1/3. There's 1/3. So 1/3, man, that was kind of a long test. 1/3 is one of my zeros. So f of 1/3 equals 0. That means 1/3 is a root. 1/3 is a root. So I have to use synthetic division again with 1/3 being the root. This is where room is not of the essence for me, and I'm just going to show some work here. I'll have to erase it later. So let's try 1/3 on it. And remember, if 1/3 is the root, then 3x minus 1 is the factor. I'm multiplying everything by 3 and making it, it's subtracting 1, all that kind of stuff. So 1/3 is the root. This is probably one of the harder problems I've kind of encountered for my own students here. 6, 16, 21, -9. We're going to divide those numbers by 3 when we add, right? So 6 divided by 3 is 2, plus that is 18, divided by 3 is 6, plus that is 27, divided by 3 is 9, and 0 is that guy right there. Now I'm going to divide these by 3 because I only have 1/3 as that root, and I'm going to multiply everything by 3 to put in the factor, so I have to divide everything by 3 for this factor here. And this is 2, 6, and 9, so that's 2x squared plus 6x plus 9 as the other factor, which is now a quadratic, which is which is very good, which is good for what, because now we don't have to use rational root theorem anymore. Okay, so this factors down to, we have 5x minus 1 times 3x minus 1 times 2x squared plus 6x plus 9 equals 0. They did ask us to find all roots and solve. So if this isn't factorable, which it doesn't look, this is not factorable. This is a quadratic formula kind of problem. You could complete the square. I don't like to do it for certain reasons of this kind of nature of the problem, so I'm going to solve using quadratic formula there. Anyway, we do know that x equals 1/5. We do know that x equals 1/3. And we do not know what x equals right here, so we get to use quadratic formula on this thing here. Maybe I did solve a little prematurely using quadratic formula for the other ones. Set this equal to 0. The discriminant here will be b squared minus 4ac. Aha, not only is it not factorable, but it's It's not even real solutions. So 36 minus 8 times 9 is 72, which is negative 36. So that doesn't mean we're done. We don't say no solution. We solve this thing. X equals negative 6 plus or minus the square root of negative 36 all over 2a, which is negative 6 plus or minus, that's 6i all over 4, which reduces to negative 3 plus or minus 3i all over 2. So those last two solutions there are long problem, at least as far as descriptions go and plugging into the calculator. X equals negative 3 plus 3i over 2. X equals negative 3 minus 3i over 2. All right, assuming I didn't make a mistake at the very end there, that's what we should pan out to get. Any questions? I'm sure you have many, for which I spent a very long time on that one problem. So let me write out that solution set for, was it this problem? Where were we? I think it was this problem up here. So x equals 1/5, 1/3, negative 3 plus or minus 3i over 2. And it was a quartic, so there should be 4 solutions. There they are. Okay, I'm going to delete all that because we got to keep moving on. Yes, we're still in our first unit talk. This has taken quite some time here. All right. All right, we're on 35. Factor each and find all the roots. They don't give us a root here, so I imagine we can factor by grouping. It looks like we can very much here. There no GCF to start, so let's go straight into it. We have 2x to the 4th that can pull out of here, and we have x plus 4. Then minus 15x squared can pull out, and we should be able to get, x plus 2, not x plus 4, x plus 2. And then when negative 15x squared pulls out, we should be able to get x plus 2 again, which it looks like we do. And as a negative 8 pulls out here, we should be able to get x plus 2 again. Otherwise, we got to use rational root theorem. And they didn't say we shouldn't use rational root theorem. I just noticed you could factor by grouping. So this now factors into 2x to the 4th minus 15x squared minus 8 times x plus 2 equals 0. I hope this can factor right here. So let's see if it does. 2x squared and x squared. This will have to be some 8 and 1. Yeah, negative 8 plus 1. That does factor. And that's x plus 2 equals 0. Yeah, I did solve the other ones prematurely, man. I'm sorry. These do say find all roots. Maybe we didn't have to earlier on. All right, what are our roots here, however? We have negative 2. We have if x squared minus 8 equals 0, then x squared equals 8. Take the square root of both sides. We get plus or minus the square root of 8. Square root of 4 times square root of 2 is 2 root 2. There we go. And then last ones here. Probably need a little more room than that. If 2x squared plus 1 equals 0, then 2x squared equals negative 1. X squared equals negative 1/2. Take the square root of both sides. X is plus or minus I times the square root of 1/2. Oh, running out of room there. Yeah, you need binder paper for this, don't you? Plus, not me. I do. Square root of 1 is 1, but I got to multiply top and bottom by root 2. So this is I times the square root of 2 over 2, like that. Okay, so those are our 5 solutions. Negative 2, 2 root 2, negative root 2, I root 2 over 2, negative I root 2 over 2. All right, there's no way I can't, there's no way I won't, no way I'll have enough room with just that. So, evaluate, oh, it just says evaluate at the given value. I'm sorry, it doesn't say factor. Whew, okay. Evaluate at the given value. Now this is, what, without a calculator or what? Negative 6, I don't know what negative 6 to the 6 is. Plus 9 times negative 6 to the 5th, plus 18 times negative 6 to the 4th, minus 5 times negative 6 cubed. I don't really know what kind of question this is, like why this is kind of within here. 18 negative 6 plus 24. Yep, calculator time, here we go. Negative 6 to the 6th. I'm going to pause it. There's no reason you need to see what I'm going to do. All right, in my calculation, I got negative 12. I hope that's correct. Equals negative 12. So that's f of negative 6. We get negative 12. All right, the same thing is going to be happening here. We're going to add m equals negative 5. I'm just going to go ahead and pause it again. We're substituting -5 into these. Well, I'll calculate it, see what I get. Sorry about that. All right, and on that answer I got, I might have to sneeze. On that answer I got 4. Okay, that's f of -5. Now, the one thing I'll mention is if you're using a calculator for those, make sure that you type it in exactly as is written. That means with the parentheses. -6 to the 6th power should be a positive number, not negative. And if you don't put parentheses around the -6, when you raise it to the 6, it'll give you a negative result. So just be very careful with that. Okay, write a polynomial function of least degree with integral coefficients that has the given zeros. Now, the thing here of integral coefficients, least degree, all this kind of stuff, it's trying to tell you that don't add roots that you don't need, but do add roots that you do need. So, for example, 2 root 2 is a root, then -2 root 2 is a root. Those are conjugates. Those are going to give you integral coefficients. When you multiply the difference of two squares, they pan out. If -I is a root, then I will be a root as well. I will be a root. So, give me 1 second, let me minimize this other thing. Okay, so we are going to get, if 2 root 2 is a root, then x minus 2 root 2 is a factor. If -2 root 2 is a root, then x plus 2 root 2 is a factor. And then x plus I here and x minus I. This is going to be like a y equals or f of x equals here. Let's do that. Let's take f of x equals. Now, these are difference of two squares. So, you know, this is a minus b times a plus b. That's going to be a squared minus b squared. So x squared minus 2 root 2 squared. 2 root 2, 2 squared is 4, root 2 squared is 2, 4 times 2 is 8. So x squared minus 8. By the way, they didn't ask us to expand this. They didn't ask us to expand this. I will. At least for these ones. And then x plus I times x minus I, that's x squared minus I squared. I squared is -1, subtract -1, that is plus 1. So, expanding a little bit more, that becomes x to the 4th plus 1x squared minus 8x squared is -7x squared, and then minus 8. That is what that is in standard form, meaning if you set this equal to 0 and solved, you would get these 4 solutions here. But I needed I for this thing to give us integral coefficients, and this is the least degree it is. It's a quartic. There are 4 of these. So there it is. All right, 1 is a root, -3 plus root 10 is a root. That means its conjugate, -3 minus root 10, would also be a root. Now, I'm bad at these when it comes to the standard form-esque stuff. I know there's a formula thing. I'm sure if I looked at it, because I did it earlier this year, I'm sure if I looked at it, I'd know exactly what it is, but I don't remember off the top of my head. So I'm going to have to just play with it practically. And I wouldn't expect my students to try and do a memorization thing either. At least I would hope that they didn't, because I don't want them to mismemorize. Anyway, the factored form would be x minus 1 here times x, and then minus these, right? So if I, you know what? There is a faster way for me to do this. Okay, I'm going to do it down here. Check this out. If x equals -3 plus root 10, and I just add the 3 over, I'll get x plus 3 equals root 10, and then I square both sides here. Then that'll give me x squared plus 6x plus 9 equals 10. Or x squared plus 6x minus 1 equals 0. Now this takes care of the -3 plus root 10 and the -3 minus root 10 together. So that's my expansion of that. I just expanded it right then and there. And I guess I could have done it with any of the other ones there, but that is my expansion of it. That's set equal to 0. That's the factorization. X squared plus 6x minus 1. That's the way I'm going to do it. Now let's keep expanding that through distribution. That's x cubed plus 6x squared minus 1x squared is plus 5x squared. Minus 1x minus 6x is -7x. And -1 times -1 is plus 1. I got to speed this up a little bit, so there it is. I don't even know if they asked me to do it in standard form, so they just did that. All right, factor each. One root has been given. So now this time they have imaginary or complex solutions here with 1 plus I being a root. Now there are two different ways you could do this, and I don't know if I want to do the first one. The first way is using 1 plus I in synthetic division with all these coefficients here, and then you got to use 1 minus I on it later, and you have to remember that these all have I's in it. I would prefer to not do that. Instead, I would prefer to figure out what the quadratic thing, if 1 plus I is a root, then 1 minus I is a root. that would mean that, you know, x equals, I mean, this is the same thing I was just talking about before. If x equals 1 plus I can subtract 1. I can square both sides, and I'll get x squared minus 2x plus 1 equals negative 1. If I add 1 over, I get x squared minus 2x plus 2 equals 0. Anyway, this is now a factor. This is a factor. If this is a factor, then I can divide this factor out from here. So instead, I'm going to divide this by x squared minus 2x plus 2. And I do that using long division. So I'm going to instead use long division with that. So I'll have x squared minus 2x plus 2 as the divisor. And here's my dividend. This is much more preferred compared to the other stuff there. X squared goes into x to the fourth, x squared times. I get x to the fourth minus 2x cubed plus 2x squared. Subtract that out. We get negative 2x cubed minus 11x squared plus 26x minus 30. I should get a remainder of 0, right? That's the goal of these being factors, or roots, I should say. Honestly, I could have used rational root theorem. I could use rational root theorem, found a rational root. Well, I can't guarantee this has rational roots, I guess. I guess there's that as well. So that way they'd, I guess, have to give us a root. Anyway, so right here, negative 2x, so negative 2x cubed, negative 2x times negative 2 is positive 4x squared, and then 2 times negative 2x is negative 4x. Subtract those, and I will get negative 15x squared plus 30x minus 30. This looks like this will pan out just fine. X squared goes to negative 15x squared negative 15 times, and multiply those. That is negative 15x squared plus 30x minus 30. Subtract that, you get a 0 remainder. So x squared minus 2x minus 15, which does have rational roots in it. So this factor is now down into, because it just asked us to factor, right? Didn't ask us to solve, but it's not a problem if I do. Hey, I solved the other ones. This is fine. So this factors into x squared minus 2x plus 2 times x squared minus 2x minus 15. It does say equals 0 there. I honestly don't know where some of my work is scattered into now. This is quite a bit. And this factors, that's x squared minus 2x plus 2, and this is x minus 5 times x plus 3. All right, that would be a full factorization. Now notice that we didn't write it as, I guess we could have. We could have written it as x minus 1 plus I, x minus 1 minus I, things like that. But this is a proper factorization of that thing right there. As far as solutions go, yeah, x equals 1 plus or minus I. We had those ones. Here's x equals 5 and x equals negative 3. Those are the 4 different solutions if we were asked to solve in that quartic. All right, this is much more the same. I mean, literally much more the same. Looks like 1 plus I is a factor, 1 is a root, therefore 1 minus I is a root. Therefore, x squared minus 2x plus 2 is something we can divide once again. I'm going to go ahead and just do that straight up right now, as this doesn't look like I can factor by grouping or no GCFs or anything like that. So I'm going to jump straight into that here. Let's see if I can go a lot faster this time. I'm probably not going to say a lot more out loud. Sorry about that. Unless there's something I can kind of bring up to you. All right, negative 7x, negative 7x. I hope it's factorable again. I don't think I'm going to use quadratic formula this time, especially since I'm not completing the square. Plus 14x squared plus minus 14. Minus 14. And again, this should, minus 14x. Again, this should give us a 0 remainder. 10x squared minus 48x. Oh, excuse me, minus 20x. I don't know why I just did that. Minus 20x plus 20. Minus 20x plus 20. Yeah, that should work out. Already kind of getting the hand cramp. Plus 10. Yeah, that's also factorable. So, 10x squared minus 20x plus 20 factor 0. Okay, so this factors into, once again, there's x squared minus 2x plus 2, and there's x squared minus 7x plus 10. And that factors into, again, x squared minus 2x plus 2 isn't factorable except for the 1 plus I and 1 minus I stuff. So this is x minus 2 times x minus 5. Another x minus 5. X from like the last problem. All right, x equals 1 plus or minus I. X equals 5. X equals 2. Okay, or the factorization, or the factorization that was right there. But I did solve there. Okay, there are those problems there and the answers. I don't know if there are problems below. Let me quickly delete these and I'll undo if there are. Hope this doesn't crash. I don't want to have to deal with too much. I'm trying to, oh, it says not responding. Give me a second, I'm going to pause. It might have crashed when I tried to delete. Oh, there it goes. Never mind, not going to pause. There are more problems. Undo. Should I move it all down? No. All right, I'm going to delete those. Okay? So here we go. Sorry about that, getting rid of those. Okay, numbers 43 and 44. Write a polynomial of least degree with integral coefficients. So same stuff as we just saw above, like numbers 39 and 40. So here we go. If these are conjugates of each other right there, and here's another set, 2 minus root 5 right there. We know we're going to have x plus root 2 times a. I mean, you know, if you don't want to work it out as a difference of two squares right here, you could do exactly what I did with the other problems here. If x equals, say, root 2 is one of the things, it's isolated. Let's square both sides right now. Now it says x squared equals, not 4, is 2. X squared equals 2, and subtract that 2 over. X squared minus 2 equals 0. That is the combination of these two guys right here. Difference of two squares, that is x squared minus 2. If I were to expand. These two here is that x minus 2 minus root 5 and x minus 2 plus root 5. But again, I'll do what I just did for the other ones right here, which is x equals 2 plus root 5. And remember, when I square both sides, whether this was plus or minus root 5, here I'll write both of them. X minus 2 equals plus or minus root 5. When I square both sides right there, the plus or minus becomes positive anyway, because that's where the two solutions come from. So x squared minus 4x plus 4 equals 5. Subtract 5 over x squared minus 4x minus 1 equals 0. So x squared minus 4x minus 1 is the distribution of that, without having to get into a 3 by 3 scenario. Whoops, not equals 0, just f of x equals. F of x equals. All right, let's expand that guy right here. And we will get f of x equals x to the 4th minus 4x cubed. Is there going to be another? I don't think so. Minus 4x cubed minus 1x squared minus 2x squared plus 8x plus 2. There's our guy. All right, number 44. Negative 2 plus root 2 and negative 2i. That means positive 2i will be 1, and negative 2 minus root 2 will be 1 there. So if x equals, yeah, this is how I'm going to do them from here on out. If x equals plus or minus 2i, we can square both sides. That'll be x equals 4i squared, which is negative 4. Excuse me, x squared equals. So x squared plus 4 equals 0. Here's a factor. That's not the answer, that's a factor. And if x equals negative 2 plus or minus root 2 right here, I add 2 over. X plus 2 equals plus or minus root 2. Square both sides. I get x squared plus 4x plus 4 equals 2. Subtract 2 over, I get x squared plus 4x plus 2 equals 0. And there's another factor. So now we get to multiply x squared plus 4 with x squared plus 4x plus 2. And in distributing that, we're going to get x to the 4th plus 4x cubed plus 2x squared plus 4x squared, that's 6x squared, plus 16x plus 8. Okay, that's in standard form. The factored form would have had these if you subtract them over. I don't know if I'm going to write it. Okay, I'm kind of in the stage where I still have twice the amount of problems I still have to do, and I'm an hour 20 in, and I don't know how much memory I have on my computer to save all this stuff. State possible rational zeros and find all rational zeros. Oh boy, rational root theorem. Okay, we're kind of almost there. Let me pause this for 1 second because I'm going to I'm gonna have a quick break. I'm gonna try and clear up some of my computer's memory and stuff as well, so I don't run out of room. Hold on. Okay, I'm back, and I think I found a good way to clear out some space. Deleting, yeah, I think I should be good on space. Now, I apologize for earlier on the whole, I was solving things when I wasn't supposed to. I was looking for the word solve on these, and I never did. I didn't see the find all rational zeros, find roots and things like that. Probably shouldn't have solved those ones earlier on. I should have kept them as they were with just factoring and I don't know how much time that took up, but man, there's a lot of problems. What I really apologize for is the lack of space. I think the main reason for it was kind of for my students, but for myself, I should have expanded these more because, I mean, I can use as much room as I want, but for my students for paper and stuff, they don't need that. I probably should have expanded these for myself. So I'm not cluttering things, deleting things down the line, having it really, all the color blindness stuff. I apologize for some of that. It wasn't very well prepared. It was something where I felt like I could just jump in and do the problems, and I could do them, but it's just a matter of can I deliver it in a presentable way for you that you most appreciate. Anyway, it's for my students. They learn the material. That's all. As long as they learn the material, right? For you guys who are interested. All right, state the possible rational zeros, then find all rational zeros. So this kind of goes, this is the rational root theorem. This goes to my P over Q talk that I did earlier right here. So P's over Q's are factors of constant over factors of leading term in standard form. So plus or minus factors of constant are 1 and 2, factors of leading term are 1. So 1 divided by 1 and 1 divided by 2. These are the 4 possible ones here. Now, I'll mention the positive ones aren't even actually possible because these are all positives right here. That means your only roots will be negative. But finding all rational zeros, and they only want rational, they don't want irrational, I'm going to use, I'm going to just test numbers. We're going to try -1 and -2. I'm not going to try positive and positive. So negative f of -1, that's -1 cubed. So -1 plus 4 is 3, minus 5 is -2, plus 2 is 0. So f of -1 gives us 0. Now, tell you what, substituting -2 here will be faster than what I'm going to do next. But what I'm going to do next is I'm going to use synthetic division, factor out x plus 1, -1 being the root, factor out x plus 1, divide it out. And then with whatever's left, we can determine if anything in there left is solvable. Because here's the thing. I don't know if there's another -1 as a root, and I kind of want to mention the multiplicities if they do exist here. So that's kind of a part of what I want to do. I want to see what the whole thing actually looks like. Okay, so using -1, this is that color blindness I was talking about. Using -1 here, I have 1, 4, 5, and 2. That's not 52, that's 5 and 2. So 1, 3, 2, and 0. So this factors into, now there was x plus 1 that we already saw, and x squared plus 3x plus 2. So that factors into x plus 2 times x plus 1. So there is another 1. So there's x equals -1 and x equals -2. But this one has what's called a multiplicity of 2, that one right there. And that will be important for when we start graphing these guys right here talking about multiplicities. That'll be kind of what we do. So, I wouldn't have found that just by substituting, unless we tried -1 again. I could have tried -1 into, well, I would have had to have factored it still. So I'm good. Yeah, that's good what I did. All right, list all the possible rational roots for this set here. My P's over Q's this time will be factors of 24 over factors of 1. So if you already know that dividing by 1 means keeping our number, then we can just write factors of 24, which are 1, 2, 3, 4, 6, 8, 12, 24. That's a lot of them. Let's test. Let's try 1. This is where if too many don't work, I'm just going to use the calculator, I guess. 1 plus 8 plus 24 is 33 minus 41. Doesn't work. 2. Oh, negative 1. I don't think negative 1 will work. 2. 8 plus 32 is okay, that doesn't that doesn't work. 3. Okay, I'm gonna use the calculator. let me plug it in. It didn't seem like it was really slow for me to plug it in last time, so let me just type it in. So x cubed minus or plus 8x squared minus 41x plus 24. Okay, so here's what's going to happen. I'm going to go ahead and with my calculator here, I'm going to ask. Let's get rid of. Oh, look, 3 works. I already found 3. So yeah, I'm just going to use that. So I don't want to plug in every single one and find out what works, right? I want to use my synthetic. Do it until it works. Use synthetic division for the rest. So 3 works. So let's see if that works. 27 plus 9 times that's 72. That's 99 minus 123, which is negative 24 plus 24 is 0. That does work. So f of 3 equals 0. So let's use 3 as a root there in synthetic division. I have 1, 8, negative 41, and 24. All right, so that factors into x. Let's see where I can fit this. I'll just do it right here. X minus 3 times x squared plus 11x minus 8. Now check this out. That's not factorable. If it's not factorable, there aren't any other rational roots. If there aren't any rational roots, then I found my one root, 3. These 2 are the roots. They didn't ask us to find other irrational zeros. They didn't say find all zeros. They said irrational. This says find all. You see that? And find rational? I'm done. These other ones are either imaginary. I don't think they are. I think they're irrational. These are irrational solutions right there. So, done. Not rational. All right. Find all roots in these ones right here. This is where I'm going to give myself some room. And let's take a look. I cannot factor by grouping, so they want us to do our P over Q stuff just like we did before. So, P's over Q's for this one. And these are unfortunate if they're just fractions, but factors of 1 over factors of 4. So plus or minus 1 over 1, 2, and 4, which is plus or minus 1, plus or minus 1/2, plus or minus 1/4. Let's start with 1 or negative 1. Hope it works out. 4 minus 8 is negative 4, plus 5 is 1, minus 1 is 0. That does work, and that's a good sign. F of 1 is 0, so let's use 1, and we get 4 minus 8 plus 5 minus 1, or not really, 4x cubed. 4. Okay, and this looks like a perfect square trinomial here. So this is x minus 1 times 4x squared minus 4x plus 1 equals 0. This guy actually does factor. This is 2x minus 1 quantity squared. That's just something I know. You can try and factor it yourself. That's the thing. So find all zeros. 1 and add 1 divided by 2. It's 1/2. This has a multiplicity of 2. Remember, being a cubic, there should be 3 solutions. 1, 2, 3. Right? 1/2 appears twice, which are rational roots, right? They actually would have worked in my test. All right, this one right here. I'm curious. This looks like it can factor by grouping, and I think I can. I just don't know what that big set is right there. I think 29 is the thing. I think that does work. All right, so let's try and factor this thing by grouping here. So 3x to the 4th leaves us with 5x plus 2 plus, I think it's 29. 29x squared. 29 times 5 is 145. So 5x plus 2 and plus, let's just hope that works, 18 and 5x plus 2. It does. All right, there's a good start. So 5x plus 2 is a factor, as well as 3x to the 4th plus 29x squared plus 18 equals 0. And they only want rational. No, they want all roots. So they do want all roots here. I'm hoping this guy here is factorable. We've already factored this this one. Let's see. 3x squared, I should say. 3x squared here and x squared here. Plus and plus. 18 can be 6 and 3 or 9 and 2. Let's try 9 and 2 because 3 is already a factor there. So let's try 9 here and 2 here. So 27 plus 2 is 29. Yes, that does work. Okay, so there that is. And they said find all zeros. Now our only rational roots seem to be these guys. If 5x plus 2 equals 0, subtract 2, so divide by 5, that's x equals negative 2/5. If these equal 0, this is where we solve using square roots. This is the stuff I started to do early on before I was supposed to. Negative 2, negative 2/3, take the square root of both sides. That's plus or minus I, root 2 over root 3. Multiply top and bottom by root 3. And that's plus or minus I root 6 over 3. Whew. Okay. And finally, hold on. Let's move that up just a little bit. And finally, x squared plus 9 equals 0. X squared equals negative 9. X equal, take the square root of both sides. X equals plus or minus I, 3i. 3i. All right, fifth power, 1, 2, 3, 4, 5 solutions there. Only one rational, rest imaginary. Okay, I can't see the rest of these problems here, so I'm going to have to delete this stuff. I'm sorry. But I believe we are done with Unit 1 material. Yep, Unit 1 material. Let's go to Unit 2. So that was about an hour and a half. Let's go to Unit 2 here. I don't know if all the other units are just as long here, but I've done about a third of the problems. So maybe another 3 hours to go. I have no idea. Sketch the general shape of each function. Now, they'd say general shape. I don't know if they're asking for roots and all that stuff, so I'm not going to do that. What I'm going to do is look at the degree of the polynomial. The degree is odd. And the leading coefficient, whether it's positive or negative. I would like more information, though, because I want to know where they cross. So do they want... maybe they want more stuff. I'm not really sure here. I know it crosses through 0, 0. I'm not really sure, but being an odd degree, here's the thing. There's something regarding number of turns that this can potentially have and where it crosses through. I don't know specifically if they want us to say where all these things cross, like all this stuff. I'm not going to go more than what they want us to do. So here's all I know as a certainty. Odd degree, positive leading coefficient means, and fifth degree, means that it can turn as many as 4 times. So it can do like a 1, 2, 3, 4, excuse me. It can have a 1, 2, 3, 4 turns there and start down and finish up. I don't know where it crosses through except for 0 because x is a common factor here. And the other solutions are imaginary, potentially. No, they're not. They're potentially irrational. So, I don't know. I don't want to dive too deep into that and kind of figure out what all the rest of that stuff is. I don't think it's worth the investment when they say general shape. So I'm just going to go and just do that. That's fine. This one, the degree is even. It's a 4th degree. And the leading coefficient is negative. Negative leading coefficient with an even degree means it's going to start down and finish down. What do you mean start from the bottom, finish at the bottom? It crosses at negative 2 for the y-axis right there. That's, I don't know. But in a 4th degree can turn 3 times. In 1, 2, 3, and finish down like that. And I don't know if that's exactly where they cross or anything like that. I have no idea. But that's the general nature of what to expect to draw when you do. The behavior, the number of turns, and potentially how many times they can cross through the x-axis. And I think that's really all that's being asked for. If it's asking for more, I'm not diving into it because of the solution sets that can be had being irrational and such. I don't think that's for that. I think that's for these problems here. State the number of terms, sketch the graph, state the real number of real zeros, things like this. Okay. These are the ones I'd prefer to solve because I have scales, I have instruction, that. All right, so number of turns. It says possible maximum number of turns. 4th degree can turn up to 3 times. Will it? Not necessarily. It can up to 3 times. Says then sketch the graph, state the number of real zeros. Okay, so let's go ahead and solve this thing. Right? If we set this equal to 0, first of all, it crosses at 0, negative 3. F of 0 is negative 3. It definitely hits there. I'm not going to find all the other relative maxes and mins, but I will find out where they cross the x-axis next by setting this equal to 0. So I have negative x to the fourth plus 4x squared plus 2x minus 3 equals 0. If I divide everything by negative 1, I get this here. Now we have to solve this thing. And, rational root theorem, it's what we're going to do. We're going to get our p's over q's out. Let's see if they exist. And if they don't, I'm not going to dive into imaginary land. I'm just going to go ahead and just sketch just some other kind of graph, but knowing, I'll show you what I will know about it, which is nice. Plus or minus 1 and 3, plus or minus 3. Let's test these out. Let's see which ones give us 0. So negative 1 plus 4 is 3, plus 2 is 5, minus 3 does not work. Negative 1 plus 4 is 3, minus 2 minus 3. Negative 1 doesn't work. Negative 81. I don't think these are going to work. So, okay. I don't think these have any real zeros. So, number of terms are 3. If 3, negative 3, 1, and negative 1 don't work, and I believe, because 81's too large for us to get back to 0 with those numbers. I think it's just too big. Let me check on 1 again. 1, negative 1 plus 4 is 3 plus 2. Yeah. Yeah, no, that doesn't work. All right, so number of real zeros here. Real zeros? 0. If I couldn't... I'm trying to think how I can say this out loud. If I didn't have any rational zeros to pull out of here with a 4th degree polynomial, then I wouldn't have any irrational... Gosh, I'm trying to think on how to say this. If I didn't have any rational zeros... Wait, can irrational zeros come out of this? Hold on, give me 1 second to think about this. Okay, sorry. So I'm struggling with myself to kind of say what I want to say here. So the first thing I wanted to state was I was kind of confusing saying real with rational here. So as far as rational zeros, there are no rational zeros. There may potentially be real zeros, though. They would just be irrational. The thing is, unless we are given irrational roots and use synthetic division or along, like what we did before to work that out, or unless it was a quadratic equation where we could use quadratic formula to solve, I am not in any business right now to talk about how this thing could potentially be graphed. So I'm not going to say for sure this is kind of an uncertainty what it looks like unless you use a graphing calculator to then look at what this will look like as far as sketching the graph. I'm not in love with the problem for integrated math 3. I'm not in love with the problem for integrated math 3 because this graph could just look like this and jump up and down and go like that, or it could like cross through one of these right here and kind of come up and down like that. And finding those irrational zeros in a quartic environment, not knowing any of the irrationals and not knowing any rationals, is not a business that we're really looking to venture into. Not in love with the problem. I apologize for the problem's nature here. I am going to move on. I'm not actually very comfortable even doing those myself. It involves something called Newton's method, and I'm not getting into that. So I'm going to move on from that problem. You can use a graphing calculator to look at what it looks like. I apologize. 52 should be a lot better, though, because of its nature. It's a cubic, which means there will definitely be a rational solution. It has a GCF. I mean, there are a lot of other things we can do with this one. Now, regarding turns here, the possible number of turns it can have is 2. Being a cubic, it can have 2 turns. Number of real zeros will come into the form of us, once again, setting this equal to 0. Negative x cubed plus 3x squared equals 0. Multiply everything by negative 1 there. X cubed minus 3x squared equals 0. Factor out x squared. X squared times x minus 3 equals 0. And this is x equals 0, x equals 3. Now 0 has a multiplicity of 2, and 3 does not. Number of real zeros, 3. There they are. 3. So number of real zeros is 3. There is 0 with a multiplicity of 2. That's 2 real zeros. And then 3 with a multiplicity of 1. Now regarding the graph itself, it is a negative cubic. So it's going to start from up here. It's going to find its way down through 0. Not through 0. It's going to bounce off of 0. With the multiplicity of 2, it's going to bounce off of that like this, like a quadratic nature. And it's going to jump up and come back down here. How tall does it actually go right here? I'm not diving into that right there. That's a kind of calculus thing. It's called a relative maximum. But it does have a relative maximum right there. Relative max, that's one of the turns. And it has a relative min right here. That's the number of turns. Anyway, that's not always something to point out, but that's something I could actually graph for you. That's something we could actually find out where it crosses here. If I found out what one of the irrational zeros were, we'd be in good business. We could find the rest. Outside of that, no, we're not doing that. All right, if those are the only ones to graph, then that's, I wish there were more that we're graphing there. Okay, evaluate each function. This is still a part of this unit, but just some new stuff in function operations. If h of n is 2n plus 5, find h of n minus 2. Now, here's what's going to happen. N minus 2 will replace n in your function. So h of n minus 2 will be 2 times n minus 2 plus 5, which is 2n minus 4 plus 5, which is 2n plus 1. This replaces your input wherever it shows up. So h of 4n on number 54, h of 4n is going to replace n here to have 4n cubed minus 4n squared, which is 64n cubed minus 16n squared. So when they ask us to find these things, they just mean evaluate it in full, combine like terms, that kind of stuff, and that's what we're going to do. All right, this one's division. Now, we're not doing rational expressions and stuff until later, so I will write it as a division and not attempt to factor further. That will be used later there. But f over g of n means f of n over g of n. It has nothing to do with multiplying n by f of n over g of n. That's just the shorthand version of that notation. So this is 3n plus 2 over n cubed minus n squared. There's something I would tend to mention on a problem like this later, which is domain restrictions. I'm going to save that for when we run into them. For now, I'll write exactly as they're asking us to do, just to do it. I saved division for later with my own students, and I'm going to do that here as well. I'm not going to be writing out what my domain restrictions are just yet. All right, this doesn't say g times f of x. That says g of f of x. See that one being a dot and that one kind of being a O, like goff right there, as opposed to g times h. That is g of f of x. So this is g of f of x right here, which means f of x will be the input in g's equation. That means we're going to be doing g of x squared minus 5. X squared minus 5 will replace x in g's equation. So negative 4 times, instead of x, it'll be x squared minus 5 minus 2, which is negative 4x squared plus 20 minus 2, which is negative 4x squared plus 18. Now I know that you can factor and stuff like that. We're not doing that. We're simplifying by expanding and combining like terms, so we are good on that one. All right, g of x plus h of x right there. That'll be 3x plus 2 plus 3x squared plus 1. Now, I'll wrap parentheses around it. It'll mean nothing, like I'm not foiling. I'm just going to stress the fact that if this said minus right here, you'd have to distribute that negative, like the first two problems on this whole thing. And I do want to write this in standard form. So I have 3x squared plus 3x plus 2 plus 1 is 3. So 3x squared plus 3x plus 3. Yes, it has a GCF of 3, but we're going to leave it. All right, g times h of t means g of t times h of t, which is going to be t minus 3. I can put h of t first. It's a particular thing that when I multiply, it's easier for me to see the larger coefficient first. So pardon me for that. It's going to go like that. Okay. So this will be 3t squared. Kind of faster foiling for me. Minus 9t minus 5t is negative 14t. And then plus 15. Okay, so those are those 4. Or however many we've done. Oh, there's some more. And no subtraction, really, to speak of. G of negative t divided by h of negative t. So it might be worth your while to actually evaluate what those two things are first before you actually write the division. Even though I guess division's not going to do much to them. But g of negative t is negative. And you know what? Was even and odd on here? I don't think so. But even and odd functions are you substitute the opposite sign right here, and you see if you get an opposite polynomial, an opposite expression out of it, like this negative t cubed plus t cubed. or plus t. Notice how that's exactly opposite of t cubed minus t. That would make this an odd function, like that. And yeah, we're not testing those apparently. So that's g of negative t. H of negative t is 4 times negative t minus 5, which is negative 4t minus 5, which is neither even nor odd. An even function would be if I substituted negative variable into there and I get the exact same thing out, which I don't. Negative 4t minus 5. So this will be g of negative t over h of negative t is negative t cubed plus t over negative 4t minus 5. And again, I'm just going to leave it like that. F plus g of x squared is f of x squared plus g of x squared. Hey, maybe it's worth your while to find out what they are first and plug them in. I'll just do it straight on this line this time. I don't think it's too bothersome. Let's see. We're going to get f of x squared is x squared squared minus 4 plus g of x squared is 4, x squared minus 3. So substituting x squared in for x right there, and then combine like terms. X squared squared is x to the 4th. And then negative 4 minus 3 is negative 7, and I have plus 4x squared right there. So there it is. Yep, not too bothersome. All right, f of g of x over 4. So I have to do f of x over 4 squared minus 5, which is f of x squared over 16 minus 5. Which is 4 times x, or x squared over 16 minus 5, plus 2. Distribute the 4. 4 times x squared over 16 is x squared over 4. 4 times negative 5 is negative 20. Plus 2 is x squared over 4 minus 18. There are a lot of ways I could have written that. 1/4 x squared minus 18. X squared minus 72 all over 4 if I wanted a common denominator. And I'll leave it. All right, thank you. H of g of a minus 3. Now, to start this, I'm going to find out what g of a minus 3 is. G of a minus 3 is a minus 3 cubed plus 2 times a minus 3. Now, a minus 3 cubed is not a cubed minus 3 cubed. It is the binomial expansion. It is 1331. 1331 of these guys right here. I mean, it's not huge, but it's just, you know, we got to do it. So a cubed plus 3 times a squared times negative 3 plus 3 times a to the first times negative 3 squared plus negative 3 cubed plus 2a minus 6. This is just for g of a minus 3, by the way. So that's a cubed minus 9a squared plus 9 times 3 is 27 plus 27a minus 27 plus 2a minus 6, which is a cubed minus 9a squared plus 29a minus 33. Okay, that's g of a minus 3. H of g of a minus 3 is h of this. So h of g of a minus 3 is h of that, which means that's got to substitute into here. So we got to do 2 times this plus 5. So let's see if we can kind of do that in kind of a faster way. So 2 times that, that's 2a cubed minus 18a squared plus 58a minus 66, and then plus 5. So negative 66 plus 5 is negative 61. If I'm going to cut some corners, there it is. Let's hope I did that all correctly without a hitch. All right, state if the given functions are inverses. Now, there are a bunch of ways we can do it. The version I'm going to do is I'm going to do g of f of x and f of g of x. I'm not going to actually find their inverses. I'm going to compose the functions and see if I get x out. Do I get g of f of x equals x and f of g of x equals x? If yes to both, inverses. If no to even one of them, not an inverse. So let's try g of f of x. That's going to be g of 3x plus 1. 3x plus 1 will substitute for x right there. 3x plus 1 minus 1 over 3. No, you can't cancel everything outright right now, you do 1 minus 1 is 0. Now you get 3x over 3. 3 over 3 is 1. You get x. Okay, that's good. F of g of x is is f of x minus 1 over 3. I mean, this should work. Is 3 times x minus 1 over 3 plus 1. 3 over 3 is 1, and that's x minus 1 plus 1. Negative 1 plus 1 is 0, and that equals x. The answer is yes. Yes, it is. All right, can't imagine this one is. I see some 2's here that aren't there, but you know what? We just got to try once, and once it breaks it, we can just say no, and then we're good. So let's try g of f of x here. That'll be g of negative 2 over x plus 2 plus 3, which is, sorry for the kind of how I'm writing it, 3 over, oh boy, x. Negative 2 over x plus 2 plus 3 plus 3. Okay, not as easy as it looks regarding what you're going to do here. I can't guarantee that this won't work. I don't think it should for any reason. But this, this is all in the denominator right here. 3 is not, see, I can't, it's hard to explain, but I want to make this one fraction before I divide by the fraction and multiply by its reciprocal. So what I'm going to do is take that negative 2 over x plus 2 plus 3. I got to multiply 3 by x plus 2 over x plus 2 right there, which is going to be 3x plus 6. So instead I want to write there 3 over negative 2 plus 3x plus 6 all over x plus 2. Now I have it as one fraction, and I can even combine like terms. Negative 2 plus 6 is 4. So that equals 3 over 3x plus 4 over x plus 2 plus 3. Dividing by this fraction is multiplying by its reciprocal. That means that the x plus 2 can come up top and multiply by that 3. 3 times x plus 2 over 3x plus 4 plus 3, which is 3x plus 6 over 3x plus 4 plus 3. Doesn't look like that thing's going to cancel out and just become x in any sort of way. Now, you cannot divide 3x with 3x or convert 6 over 4 and anything like that. Nothing like that can cancel. A lot of my students do that. No, you cannot do that. However, this is a big fat no. Maybe you could have looked at that and seen it for yourself. Just this will not simplify to become 1. I've actually kind of cleaned it up as much as I feel I should have been able to, outside of multiplying this by 3x plus 4 over 3x plus 4, which would give me 9x plus 12, 12x plus 18 over 3x plus 4. No, that would not have panned out. So no. Anyway, but yeah, no big canceling to happen there like a lot of my students would end up doing there. All right, find the inverse of each function. To find an inverse, you swap x and y, and you solve for y all over again. So f of x is y. Let's take the inverse by swapping x and y. Here is the inverse, but let's get y by itself now. Let's add 1 to both sides. X plus 1 equals 1/2 y. Let's multiply both sides by 2, where I'll get y equals 2x plus 2 times 2 times 2. And then that gives me inverse of f of x equals 2x plus 2. There is the inverse of that guy. This one's going to be a lot faster, I believe. G of x is y. Swap x and y. X equals negative y plus 5. If I add y and subtract x, I'll get y. Whoops. I'll get y equals negative x plus 5, or inverse. Hey, it's the same answer. That's cool, huh? Why are they inverses of each other? Because the way they reflect across the line y equals x, they actually would be. They're the same thing. It's kind of weird, but it works. And we're going to kind of look at inverse stuff right here. Find the inverses of each, then graph the function and its inverse. Now, I'm going to talk about these in a lot of different ways here, because we got to start graphing cube roots. Find the inverse of each function, graph the function and its inverse. So let's find the inverse. You know what? Let's graph the original first. Cube root of n minus 1 minus 2. This x is our n, and this is h of n right here. So right here, we have an hk, not this h, but an hk of 1, negative 2. This is our center. We're going to start at 1, negative 2. As a cube root with a stretch factor of 1, we can go up 1 over 1. Let's go over 1 up 1 and over 8 up 2. I can't really fit that, but pretend like I could, which is actually probably a little farther out right there. And then left 1 down 1 and left 8 down 2. I can kind of pretend like I can fit that right there. So this graph should look something like this. It doesn't actually flatten out, but it kind of has that sharpness to it right there. That's right. That's pretty good. Okay. So there's the cube root one. Now, if I were to graph, they do say find the inverse, and I will. But if I were to graph this on my own without finding the inverse, we would reflect across the line y equals x, which means any x becomes a y and any y becomes an x. So our next graph should look like this. See how this is 1, -2? We're going to have a -2, 1 center. See how this is 2, -1? We're going to have a -1, 2 point. This is 0, -3. We'll have a -3, 0 point. This would have been all the way out at 9, 0. So there should be a point up here that's going to be at 0, 9. And there's a point over here that's at -7, -4. So there's going to be a point here that's at -4, -7. So our graph will do this right here, like that, and be pretty sharp. I didn't do that very well. Be pretty sharp like that. So that's what our graph will look like. Let's confirm that. Let's do y equals, I don't like that these are not x's, n minus 1 minus 2. Swap that. N equals cube root of y minus 1 minus 2. Let's solve for y here. Add 2 over. N plus 2 equals cube root of y minus 1. Let's cube both sides. Now, I'm not going to actually expand this cubic. I want to keep it in its like vertex form. Not really vertex form, but the graphing form right there. So that's y minus 1 equals n plus 2. N plus 2 quantity cubed. Add 1 over, you'll get y equals n plus 2 quantity cubed plus 1 plus 1, or inverse of h of n equals n plus 2 quantity cubed plus 1. And that is the inverse right there. Okay. Now, that guy's center, its hk is at -2, 1, which is right there, -2, 1. And then this has a stretch factor of 1, and like a cubic does, it'll go 1, 1, 2, 8. 2, 8 there is at 0, 9. And then -1, -1, -2, -8 right there. So that is the graph of the cubic. All right, let's move forward to number 68. Let's do the same thing. This is a rational function. So actually, as far as graphing goes, we're going to have to graph rational kind of early on. Okay. I'm going to find the inverse first, I suppose, here. So this will be, it's n again. Not my favorite. N and g of n. All right, y equals 2 over n minus 2 minus 2. Let's swap n and y. N equals 2 over y minus 2 minus 2. Let's add 2 over. N plus 2 equals 2 over y minus 2. We're going to multiply both sides by y minus 2. And at the same time, let's divide both sides by n plus 2. So boom, 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 boom. That basically they switch places. So y minus 2 equals 2 over n plus 2. And add 2 over, y equals 2 over n plus 2 plus 2. Or inverse of g of n equals 2 over n plus 2 plus 2. Okay, there's the inverse. Now let's graph them both and kind of see what's going on here. So this one has, this is the a over x minus h plus k form. And I'm going to graph it with that in mind. I think that's just my go about here. So my vertical asymptote, and I know this isn't quite the unit that we're on right now, talking about rationals, but it's here. So I have a vertical at x equals 2, or n equals 2. Vertical at x equals 2 right there, vertical asymptote right there, domain restriction. Horizontal asymptote at y equals -2, or g of n equals -2. Right there. And then a stretch factor of 2 means 2 divided by 1 is 2, 2 divided by 2 is 1, 2 divided by 4 is 1/2, 2 divided by 1/2 is 4, kind of like that. And I can get this graph going. I guess I'm not going to speak too much on it right now, as long as I'm not really in that unit of sorts, but this is the basic graph that I can get out from this guy right here. Hey, the problem was provided. Don't shoot the messenger. Don't shoot the video creator. So there's that guy. Now the one in purple right here, if I reflect across the line y equals x, then you could probably come up with points right there. I'm just going to go ahead and graph this other one, and then maybe we can see if it reflected across just fine. So let's go ahead and do that one over here with x equals -2 and y equals +2 as my asymptotes right here. Okay. And then this 2 is still the same thing. 2 divided by 1, 2 divided by 2, 2 divided by 4, 2 divided by 8, 2 divided by 1/2, 2 divided by -1, 2 divided by -2, 2 divided by -4, 2 divided by -1/2, 2 divided by -1/4. All right, so I can get a graph here that's looking like in purple. I mean, it's a lot of things to graph the function and its inverse in something like this with these rationals. I don't think I did these with my students because we did these before we were graphing rationals, so we never went back to the inverses. But if you kind of look, if you tilt your head, I guess I got to look this way for you. If you tilt your head, then you'll see the symmetry going across, kind of like right there. Looks kind of funky, but that is what those graphs look like. You know, you don't, here, let me get rid of the asymptotes, see, and turn them into black and white and see if you can kind of notice it a little bit better. So now turn your head and see the symmetry going across right there. You see that symmetry when you tilt your head there? Kind of cool, huh? Anyway, those are the two graphs that you saw, but I'm going to bring them all back because that's how I would have graphed it. Okay, that's kind of the end of that unit, it looks like, unless we're kind of moving on. Now, this is a part of our most recent unit that we did right here. So it looks like we're skipping the rational things for now and we're saving them for the end. I remember it was kind of saving them for the end. So let's just go in the order that we have them. Use absolute value signs when necessary. Now that's something where, oh boy, I haven't been doing that with my students. I got to decide whether or not I'm going to do it. I am and I'm not. I'm going to have a version for my students and a version for you guys and explain the difference between the two. It has to do with when we use variables. It has to do with when we use variables, and it doesn't always happen. All right, this is -6 times square root of 32 is root 16 times root 2. I'm not going to get deep into that. I'm going to do it for this problem. After that, I probably will not. -24 root 2. That's the simplification. All right, this one, square root of these things. Now, the square root of 8 is 2 root 2. Root 4 times root 2 is 2 root 2. Square root of x to the fourth is x squared, not because the square root of 4, but because 4 divided by 2, and same thing for y. Now, I don't need absolute values around these because we're still squaring something, which means they'll stay positive regardless there. So that becomes 10x squared y squared root 2, like that. All right, number 71, simplify. I have nothing to simplify as far as radicals go, but I can kind of combine like terms. -1 root 3 plus 2 root 3 is 1 root 3. So 3 root 2 plus 1 root 3, and that's all we get. We're done with that problem. Same thing right here. -root 5 plus 3 root 5, that's 2 root 5. So this is 2 root 3 plus 2 root 5, and we're actually done with that problem as well. Good, I need some problems like that. All right, fourth roots. I can't take the fourth roots of these. I imagine I could take the fourth roots of these. I'm not sure because 486, what's a perfect fourth power? 16. This does not divide by 16. 81. It does divide by 81 though. So 486 equals 81 times 6. So fourth root of those, and the fourth root of 81 is 3. So this becomes -3 times the fourth root of 3 minus 3 times the fourth root of 6 plus, now 3 times the fourth root of 6 is 9 times the fourth root of 6. Now I could have combined those first and then simplified, but I'm just going to go and leave it like that. Minus 3 times the fourth root of 3. So this becomes -3 minus 3 is -6 times the fourth root of 3, and then -3 plus 9 is +6 times the fourth root of 6. So there is that. All right, cube roots. Cube roots. Cube root of 108. So 108 is not a perfect cube, but 27 is. 108 is 27 times 4. So cube root of those. And that will be 3 times the cube root of 4. So 3 times the cube root of 4 times 2 is 6 times the cube root of 4 plus 2 times the cube root of 4 plus 135. What are my other cube roots? I got 20. 27 still works. So 27. So 135 is 27 times 5. So cube root of those is 3 times the cube root of 5. So 2 times 3 is 6 times the cube root of 5 plus, now 24 is 8 times 3. Cube root of 8 is 2. So 2 times the cube root of 3 times 3 is 6 times the cube root of 3. Okay. Combine those. Only these two can combine right here. So that becomes 8 times the cube root of 4 plus 6 times the cube root of 5 plus 6 times the cube root of 3. I think I got that one correct. I'm not certain. I think that's it. All right. Number 75. Right here. Now, this is where there's going to be a little bit of a hiccup. We tend to know that the square root of x squared equals x. Sort of. They do cancel. However, you remember that if you square a number, right? If I say, hey, what's the square root of 9 squared? Is that 9? Yeah, sort of. But you have to remember the square root of negative 9 squared is also 9. Because negative 9 squared is 81. Square root of that is still 9. Who's to say whether this was a positive or negative 9, right? So how do we know which one it is? Well, it's really, we don't. The idea is that we don't know which one this was that gets us 9, so who knows if it was positive or negative 9? What if we took the absolute value of our numbers? Because absolute value of 9 is 9, absolute value of negative 9 is 9. So square root of x squared isn't x, it's the absolute value of x, because you don't know if that number was going to be a positive or negative 9 that you had to square to begin with inside of there, right? So who's to say which one it would have been, unless you know your variable was positive. So whenever I've done this with my students, x, y, z, etc., they were never negative. We always just assumed they were positive exponents. So there's one version that we'll do for the masses, and one version I'll do for my students here. I don't know if I'm going to do this each time. I guess I got to do it each time for these problems. So 5 times the square root of x squared is the absolute value of x times the square root of 3 times root 6x. Root 3 times root 6x is root 18x. So, and that can actually simplify. So 5 times the absolute of x times root 18x. 18, square root of 18 is 3 root 2. 3 times 5 is 15. That becomes 15 times absolute value of x root 2x. That would be an answer. Or if x was positive, it would be 15x root 2x. The only difference is putting the absolute value versus not. And you put it in when we take the square root of a quadratic. Really, that's going to be the time when we do it. Depends on if things can clean up, though. Like this one can possibly clean up a little bit. So why don't I do this on this next one here? Before simplifying first, let's multiply everything together. I think the numbers are small enough that we can do that. Maybe other times we shouldn't do that. All right, so 3 times 12 is 36. We'll get the square root of 36 and then r to the 4th, and that becomes 6r squared. There is no absolute value this time because squaring it negative and raising a negative to the 4th still gets you positives regardless. That problem's actually done. All right, this one we get to distribute. Root 15 times root 6 is root 90. Root 15 times root 5a is root 75a. Square root of 90 is root 4. 9 times 10. I'm sorry. I don't know why that was too slow for me. 3 root 10 plus, and this is root 25 times root 3, so 5 root 3. 5 root 3a. And I'm actually done right there. That's all I can do. 10p distributing into here. That, or root 10p. That is root 50p plus 3 times root 20p squared. 3 times root 20p squared. Now root 50p is root 25 times root 2p, so 5 root 2p, 5 root 2p, plus, and this has 4 times 5, root 4 times root 5 is 2 root 5, 2p root 5, 2 times the absolute value of p root 5. So, let's start with the numbers. So 2 root 5 times 3 is 6 root 5. So 6 root 5, and then the absolute square root of p squared is the absolute value of p. 6 times the absolute value of p, root 5. Or for my students, I'm just going to put 5 root 2p plus 6p root 5. Again, don't worry about absolute values for our math students. Okay. I hope you understand what I'm saying with it, though. See, that's the problem, being contradictory to, not to actual math. We were just working with them assuming variables were positive. And a lot of sites do that. They'll just say assume the variable's positive, work it out. This says use absolute values if necessary. So I'm following what you might see on an answer key or what your teacher may be doing with you. Or what you'll probably see in pre-calc and whatever you do from there. All right, we got to FOIL this thing here. Not much on room, but let's go for it. Negative 3 root 3n. And here's the thing. I'll say this. With these problems, I wasn't using variables with my students. My students are probably going to, I'm probably going to skip those problems with my students anyway, including this one, because it has a variable. It's a little more to talk about. We've done other simplifying ones with variables, and it just wasn't these ones. So there's that. All right, negative 3 times 3 is negative 9. Root 3 times root 3 is 3. Negative 9 times 3 is negative 27. That's our first term. Negative 27 root n. The n never escaped the radical. Everything else did. Negative 3 times root 3n, that's negative 3 times 3, which is negative 9 root n. Root 2 times root 3 is root 6, so that's plus 3 root 6. Root 2 times root 3 is plus root 6. Okay, and that becomes negative 27n minus 9n is negative, or root n, is negative 36 root n. Plus 3 root 6 plus root 6 is 4 root 6. Okay. I was wondering why these problems were a little different. I'm like, I'm not doing these with my students at all. All right, so boom, boom. And it depends on if your teacher's using the absolute value thing or not. So I could say not even for my students, for some of you guys as well. All right, again, save the n for last. Negative 5 root 3 times root 3 is negative 5 times 3, which is negative 15. So it's negative 15 root n. The n never escaped. This is going to be negative 5 times 2 is negative 10. Root 3 times root 5 is root 15. That doesn't have any perfect squares there. So negative 10 root 15. And n, root n times root n is root n squared, which is the absolute value of n. So here we go. So negative 10 times the absolute value of n times the square root of 15. 2 times root 5n times root 3, that's root 15n. So 2 root 15n. And 2 root 5n times 2 root 5n is 4 times 5 is 20 times root n squared is the absolute value of n. So plus 20 times the absolute value of n. I don't think anything there can combine. So I'm going to leave it just like that right there. Now for the ones who are treating all exponents positive, that's negative 15 root n minus 10 n root 15 plus 2 root 15n plus 20n. That's with variables positive. All right, number 81, the square root of 25 is 5. The square root of 16 is 4. It's kind of a weird problem, which is 5 over 8, and we're done. That's probably not what's expected. These problems are probably not written the way they were intended to. What was probably intended to do was rationalize denominators, and it's already a perfect square, and that's a perfect square, and that's a perfect fourth power, and that's a perfect square. I don't know if these problems were meant to be the way that they are written, but that's okay. Let's do what they're given. 5 times root 25 is 5 times 5 over root 16 is 4. That's 25 over 4. I mean, hey, if it speeds up the problems, there it is. This is 2 minus 4th root of 3 over 5 times 4th root of 81 is 3. So that's 2 minus 4th root of 3 over 15. Again, apologize. This is not the way. See, the way these problems are probably intended to go is rationalizing denominators. Multiply top and bottom by something that would make it happen. These don't need that. So I'm just going to leave them. Why not? There's nothing to reduce either. So root 2 minus root 3 over 5 times 2, which is root 2. I'm smiling because of the nature of the problems. I mean, I would have thought hard about creating these in a different way, but that's okay. These problems need us to do more, and suddenly they kind of throw them at you like, okay, suddenly, good luck. To rationalize this denominator here, I can't just multiply top and bottom by root 3 because that has to distribute into both of these. Although that rationalizes, that won't. I got to multiply top and bottom by this conjugate here. Now, we've seen a couple things with conjugates a little bit before, difference of two squares. I did not mean to write a 3 there. Negative 1 plus root 3 over negative 1 plus root 3 keeps the value the same, but it gives us a rational denominator, which is what we want here. Now on top, we're going to distribute, and we'll have negative 3 plus 3 root 3. And on bottom, we're going to have 1 squared minus root 3 squared. 1 squared minus root 3 squared. And that's negative 3 plus 3 root 3 over negative 2. Now you don't want a negative denominator, so if I take that negative and shove it up this numerator right here, I will distribute it into both of these, so it'll become 3 minus 3 root 3 all over positive 2. And that's the way an answer key would probably show that answer. When I say probably, I mean they would show it that way. All right, number 86. Same thing. Let's multiply top and bottom by the conjugate of the denominator to rationalize. No, these do not cancel. No, you don't multiply top and bottom by root 5 over root 5. But you multiply it by 3 plus 4 root 5 over 3 plus... And no, you don't square both sides. Or square top and bottom. There are many reasons into all those. Basically, it's not correct math. That would change your value. Some are incorrect as far as how values would be applied. All right. Difference of two squares on bottom, but on top we distribute. We have 3 root 5 plus 4 times root 5 times root 5. That's plus 4 times 5. That's 20. Plus 20. All over 3 squared, 9, minus 4 root 5 squared. 4 squared is 16. Root 5 squared is 5. 16 times 5 is 80. 9 minus 80, which is 3 root 5 plus 20 over negative 71. Again, no negative in the denominator, please. Excuse me, which is negative 3 root 5 minus 20 all over positive 71. Distribute that negative into the top, factor it out of the bottom, and you are good to go. Let's see if there are more of these. 86. Oh, yeah. So now we have binomials with these things. Again, rationalizing the denominator. No different as far as multiplying top and bottom by that denominator's thing. But now we got a FOIL on the top, which is where I get to just keep practicing that. 5 minus 3 root 2 over 5 minus 3 root 2. Now when we, remember everything here is like distributing and such. The difference is the bottom is a difference of two squares. The top is not a difference of two squares. So that's the foiling going on there, right? On the bottom is 25 minus 9 times 2, which is 18. 25 minus 18. On the top we have 10 minus, is that a 3? Yeah, minus 6 root 2 plus 10 root 2. Minus 6 root 2 plus 10 root 2 plus 4 root 2. And then 2, negative 3. So negative 6 times 2 is minus 12. So this will become negative 2 plus 4 root 2 over 7. I'm saving time on the foiling if I'm doing it right. I'm saving time on the foiling now. All right, last one of this kind. Multiply by 2 minus root 3 over 2 minus root 3. So again, kind of a foiling process going on here. On the bottom, we're going to have 2 squared is 4 minus root 3 squared is 3. 4 minus 3, which is 1. So we're not really dividing by anything. I won't need the fraction after this. On top, we're going to FOIL. 4 root 5 times 2 is 8 root 5. 4 root 5 times negative root 3 is negative 4 root 15. Negative 3 root 2 times 2 is negative 6 root 2. And negative 3 root 2 times negative root 3 is positive 3 root 6. So nothing simplifies on top here. So this will just become 8 root 5 minus 4 root 15 minus 6 root 2 plus 3 root 6 over 1, right? So no change there. All right. Write each expression in radical form. Now I have a negative exponent and to the 5/6 power. Let's deal with the negative exponent first. That becomes 1 over x to the 5/6 power. Radical form, the 6 becomes the radical. The 5 remains the exponent, so 6th root of x to the 5th like that, and that would be your result. You don't want the negative exponent anymore as well, and that's just a portion of it. All right, number 90 here, 4n to the 4/3 power. Now that does become the cube root of 4n to the 4th power. Now I do have still that 4 to the 4th power there. We can probably, that might just be the answer. We can probably leave it like that. If I don't want parentheses around that, I can raise both of these to the 4th power. So the cube root of 256n to the 4th power, either or this. I don't know which one they kind of want. They just said radical form. This is radical form. I just know I don't want a negative exponent here or anything like that. So I'd really like to write it like this on that problem. I don't know if they want us to also rationalize this denominator. I'm not looking to do that. They didn't say, so I'm not going to. All right, write each expression in exponential form. Now, if you notice, they show the root first and the exponent second, which is something you can totally do. That's actually how we tend to kind of do some of these. Anyway, I think they're just asking us to convert, really. I might be going above and beyond on like that part here, right? So right here, this is 10x to the 5/3 power, but all of 10x is being cube rooted and raised to the 5th. So you have to have it in parentheses. Like, I'm going to leave it like that. I think that's all they kind of just want and you're done. I'm not going to do 10 to the 5th power separately this time or anything like that. But yeah, that's it. You do need parentheses around it. Excuse me, I bit my tongue. And same thing here. It's really no difference on this problem from the problem before it. So I'm just going to do that. 7x to the 5/3 power. Not much different. Okay, simplify. So simplifying, I got a power to a power here, which means the exponents will multiply. This becomes n to the 4th times negative 3/2 power. By the way, here when I simplify, I definitely can't have negative exponents. 4 divided by 2 is 2 times negative 3 is negative 6. So this becomes n to the negative 6 power. That's 1 over n to the 6th power. So 27x to the 6th to the 5/3 power here. You can do a couple things. I will rewrite this in radical form and work it that way. 27x to the 6th. We're going to take the cube root of it and raise it to the 5th power. Cube root of 27 is 3. Cube root of x to the 6th is actually x squared. Divide the 6 by 2 and raise that to the 5th power. 3 to the 5th is 243, and x squared to the 5th is x to the 10th as you multiply the 2 with the 5. That is simplifying. You don't want parentheses in your final answer at all, so that's kind of what I'm doing there. 100n to the 4th to the 1/2 power is, again, taking the square root of, and I'm just being careful because you don't want to, like, you can distribute the 1/2 power for both of these, but we're not taking half of 100. We are taking the square root of 100, and that's the difference. That's why maybe radical form might help you better write that as 10n squared instead of like 50n squared by accident, doing something like that. Negative 343v to the negative 1/3 power. I do like taking care of this negative first just because I don't like negative with our roots. So maybe I'll write it as 1 over cube root, there we go, of 343v cubed, like that. Cube root of 343 is, I think, 7, and so that's 7v. 3 divided by 3 is 1 right there, so it's 1 over 7v. Number 97, we're still like 50 problems away from being done. 64k squared to the 3/2 power. Again, just more of the same, just kind of working these things out. That is the square root of 64k squared, and then we're cubing. By the way, notice how they did not ask us this time to have absolute value exponents or variables and things like that. I'm not doing that here. So that's going to be 8k cubed. 8 cubed, I think, is 512. Sorry if it's the wrong number. I believe it's 512. And then k cubed is exactly that. Let me make sure I did all that right. Square root of, and then cubed. Yes. And then 100k squared 3/2 power is the square root of 100k squared and being cubed, which is 10k cubed, which is 1000k cubed, like that. That is a 1000. Sorry about the kind of look on that. All right, simplify. Your answer should contain only positive exponents, which was true about the things before, but I think because this is so, you kind of really need to work that. Now, a couple things I can do right here. These are not, I don't really do the problems like these with my students where it's kind of, it's hard to explain. If you see me do problems in videos, we've done different kinds now with these fraction things, but that's okay. Let's do them. Just be careful in your order of operations and how things evaluate. Raising something to the negative 1st power would actually mean flipping that whole fraction around, so I'm just going to start with that. 4 times 2 to the negative 4th over 2 to the negative 2nd power. Now, I'm personally a fan of turning negative exponents positive in fractions immediately if possible. And to turn it positive, you got to move it to the other part of the fraction. So that'll go down. This will come up. and we will end up having 4 times 2 squared over 2 to the positive 4th power. Now, before I actually evaluate these, which I could, like 2 squared is 4, 2 to the 4th is 16, all that, let's work these like they were variables here. Let's remove all 2 2's from the top. Let's remove 2 of the 2's from the bottom, and I'll have 2 squared. So I'll have 4 over 4, which is 1. That's kind of a nicer way to do it, using the properties and kind of cleaning it up, and yeah, it seemed to work out there. Number 100, 2 to the 0 is 1, and multiplied by anything means I don't really need it there. And all of these are 2's inside of it. Now, there is cubing it, but let's simplify the inside before doing that. And in doing so, let's move this 2 to the negative first up to become 2 to the positive first. So 2 to the first times 2 to the 4th times 2 to the 4th is being cubed. This has the exponents add. This will be 2 to the 1 plus 4 plus 4. That's 2 to the 9th. And 2 to the 9th is being cubed, which is 2 to the 27th. I do not know what that is. That number is way too large. I'm gonna copy and paste it in here if it's small enough that it can. I'm gonna leave it like this. Oh, actually, oh, that's not huge. I thought it was gonna be like trillions. Okay, so it's close. 134 billion. I mean, when I mean trillions, I mean like gazillions. All right, it's that number. 134,217,728. Near the billions, at least. Okay, but that's what it is. We got to do that. Okay, a squared, b squared. I should have known it was actually smaller. I knew it was smaller than million, actually. Okay, this time we got to work with variables, and this is where, well, not too much. A to the 0 is 1. 1 to the negative 4th is still just 1. I'm just getting rid of that. These will go down, however. You know what? As long as it's not a fraction, I'm not going to deal with it just yet. Let's do this. A squared b squared times 2, a to the negative first, b to the negative 4th. So that's going to be 2a squared times a to the negative first times b squared times b to the negative 4th. Now, you could bring these down here. I just said if there isn't a fraction, maybe you don't necessarily. We could add the exponents then. Listen, a lot of ways to do the problems, right? This isn't necessarily how I do it. It's just a way I want to teach it. 2 minus 1, or 2 plus negative 1 is 2 minus 1, which is 1. That's 2a. And that's b to the negative 2nd power, 2 minus 4. Now I got to bring that thing down for sure, which is 2a over b squared, like that. And finally, from this set here, this is where a fraction kind of stays a fraction. Now, negative 3 times negative 1 is positive 3. So I'm going to keep this as y cubed, and it actually stays down here. I'm not going to bring it up just to bring it back down again. This y to the negative third will go down and become y to the positive third. This will go down and become y to the positive third, and this will go down and become x to the first. So the only thing on top now is just x squared. On bottom, we have x to the first, y cubed, y cubed, y cubed. And those threes are going to add to get y to the 9th. So we'll have x, and x squared divided by x is x. So I have x over y to the 9th, like that. Okay. All right, simplify. Your answer should contain only positive exponents with no fractional exponents in the denominator. They didn't say you can't have fractional exponents, period. These are not problems I would generally do with my students in this way. I got to think about how I'm going to conjure this best when it comes to the appearance of the answer, because I'm used to converting things into radical form. I'm used to, so there are probably a couple ways I will write final answers here. Let's start by joining things as best as we can, like 3 times 2 times 4. That's 24. Then I have my x's. X to the 2/3 times x to the 0, I'm going to ignore that, times x to the negative first, times, and everything here is multiplying, but I'm kind of separating them by appearance here. I have y to the negative 3/2 times y squared times y to the 1/2. Now these exponents will end up adding together, so I got to do 2/3 minus 1. Some people might know that as negative 1/3 immediately, but if you want a common denominator here, that'll be negative 3/3. And then right here, the y, you know what? I'm going to even just write it like this, just to show that they subtract. Minus 3/3 And then the y's, we're going to have negative 3 halves. 2 is 4 halves. And then plus 1 half right there. So now I have 24x to the negative 1/3 power times y to the, I think to the first. 1 half plus 1 half is 1. Yeah, y to the first power here. So now I have 24y over x to the 1/3. Now this is not a final answer. They did ask us to have positive exponents, which is correct, but no fractional exponents in the denominator because, well, here's why. Because 24y over cube root of x. That is an irrational denominator. Now, you do not rationalize this by multiplying by cube root of x over cube root of x. That would just be cube root of x squared. That's why you have to multiply top and bottom by something else. And the fraction exponent actually helps me figure that out. I need to basically turn this into 1. So I need to multiply by x to the 2/3 over x to the 2/3 because 1/3 plus 2/3 is 1. So the denominator will rationalize to that. So this will become, this is how I would have answered it as well. 24x to the 2/3 y all over x. And you don't want to subtract these anymore because it'll bring you right back to where you were. So this is good. This is a way to answer it. I personally like this one more, 24y times the cube root of x squared all over x. I think it better formulates the concept that these two things can't interact with each other or you don't want them to. And then that's it. You're good right there. And that's a cube root, by the way. That's not y cubed. So 24y times cube root of x squared all over x. So that's how I wanted to formulate my answers there. All right, that is 103. 104, which actually looks a lot smaller. 3 times 2 is 6. Y to the 0 times y is y over x squared, it looks like. I'm actually done with that one. Okay. This one looks very fun. Well, negative 2, well, this is 1. Let's get rid of that. Okay. The x to the negative second I'm going to bring down below to become x squared. So I do have a y on top. So I have a y on top. Right here, I'm going to take the negative 2/3 and let's kind of distribute it into these. Let's see what's going on there. That's x, I don't know if that's the best practice right now. That's x to the negative 4/3, maybe it is, times y to the 4/9, positive 4/9. And then there's that other x squared, by the way. There's the other x squared, by the way. Let's interact, before bringing this up, because I'm going to subtract those again, let's interact the x to the negative 4/3 with x squared, excuse me. So that'll become y on top over y to the 4/9. And you know, I still got to work y over y to the 4/9 in a way, because I can kind of subtract those. Let's actually do that as well. Give me 1 second. So y to the 9/9 over y to the 4/9 and x to the negative 4/3 times x to the 6/3. So 9/9 over 4/9 is 5/9. Y to the 5/9 is in the numerator. This is x to the 2/3 in the denominator. Now, y to the 5/9 in the numerator is appropriate. 2/3 in the denominator is not. So we got to multiply that by x to the 1/3 over x to the 1/3. And that'll become x to the 1/3 times y to the 5/9 all over x. Now that's one version of an answer. My version I prefer will be in radical form. So that is the cube root of x times the 9th root of y to the 5th, all divided by x. Oh, whew. Okay. Last one. Oh, well. Yes, last one for these. 106. I was fine with distributing the negative into those by multiplying those. That was fine. So let's try that again. So that's m. This will be m to the negative 5/12 times n to the negative 1/6 times m to the 2/3. 4/6 is 2/3 times n to the negative 2 times 1/2 is negative first, divided by these guys here. Maybe I could clean some of these up early. Nah. Yeah. Nah. m to the fourth, n to the 3/4. I mean, everything here is multiplying. Don't confuse some things that are with some things that are not or anything like that. What's that dot? I have no idea. Delete that. I don't know what that is. N to the 3/4 times m to the negative 2/3 times n squared. Okay. I mean, I know I just don't know if I want to turn things positive first. Yeah. Let's just work the top separately from the bottom and then see where we go from there. So on the top I have, I don't know. Yeah, this is rough. This is rough. Let's turn negative exponents positive. So m to the negative 2/3 will come up. I'll get m to the 2/3 times, I have another m to the 2/3 there. Everything else is going down, it looks like. So this goes down, m to the 5/2. That one up. That's the only m that's down there, I think, now. Oh, m to the 4th. And then n's. I have still down below n to the 3/4, n squared, and now n to the negative 1/6, and n to the negative 1st. Whew. Not my favorite problem, I'll be honest. Some problems are good. These I don't like fractions any more than you guys do, guys. Okay, this is m to the 4/3 on top. On bottom, 4 is also 8/2. 8/2 plus 5/2 is 13/2. That's a 13. And okay, 4 and 6 have a GCF of 12, or LCM of 12. So this is 3/4 is 9/12 plus 2 would be 24/12 minus 2/12 minus 12/12. So that'll be 33 minus 2 is 31 minus that is 19. N to the 19/12, I believe. Oh my goodness. Okay. Not done with m still. We got to subtract these, so we got to get a common denominator for those ones. That'll be m to the, and I'm doing this kind of as fast as I can, I'll be honest. I'm not doing it much. I wouldn't do it much faster myself without saying these out loud. 8/6 minus 39/6. I'm subtracting those exponents, getting common denominator, over n to the 19/12, which is m to the negative 31/6 over n to the 19/12, which is, I hope I might have messed up somewhere, I'm not sure where. 1 over m to the 31/6 times n to the 19/12. And we're not done because we have to multiply top and bottom by something here to rationalize these. I need to complete, let's see, I need to basically turn these into whole numbers. I just need to turn them into whole numbers. So if I get 36/6, that'll be good. So I need to multiply by 5/6 and 5/6 for m. And for n, I need to multiply by 5/12 and 5/12 because we're going to add those. So on top, I'm going to have that exactly, m to the 5/6, n to the 5/12. And on bottom, 5/6 plus 31/6 is 36/6, which is 6. And then here I have 24/12, which is 2, so n squared. So that's one version of an answer. If I did that right, that's one version of an answer. If I radicalize those, I'll have 6th root of m to the 5th times the 12th root of n to the 5th, all divided by m to the 6th times n squared. Whoops. M to the 6th n squared. I don't know if that's right or wrong. I tried. I might have messed up on a fraction somewhere, but that is problem 106. Oh boy. Okay. Moving forward. We got a drink. All right. Solve each equation. Check for extraneous solutions here. Now I have, I'm going to isolate this radical because dividing by 3 will actually help me out right here. That'll give me 7. So 7 equals square root of b over 2. If I square both sides then, I will get 49 equals b over 2. Multiply both sides by 2, I get b equals 98. Checking for extraneous solutions there, 98 over 2 is 49. Square root of that is 7 times 3 is 21. That works. All right, I have isolated radicals right here, which is what I would want to have. When I square both sides here, it cancels out the radicals. I get x minus 4 equals 14 minus x. If I add x to both sides, I get 2x. If I add 4 to both sides, I get 18. Divide both sides by 2, I get x equals 9. Double checking that, 9 minus 4 is 5, square root of 5. 14 minus 9 is 5, square root of 5. That checks out. Problem 109, square root of 2v minus 9 equals v minus 6. You square both sides like that. When the radical's isolated, that's when it works out in your benefit. So you actually cancel out the radical. Got a perfect square trinomial in v squared minus 12v plus 36. I can set everything equal to 0 and get v squared minus 14v plus 45 equals 0. That factors into v minus 9 times v minus 5 equals 0. That's a 5. Sorry about that. And that's v equals 9. Oh, not x. v equals 9. v equals 5. Let's check for extraneous solutions here. That's 18 minus 9 is 9. Square root of 9 is 3. 9 minus 6 is 3. That checks out. 10 minus 9 for 5. 10 minus 9 is 1. Square root of that is 1. 5 minus 6 is negative 1. That does not work. That is extraneous. So only v equals 9 works out there. That is a v. All right, square both sides again. Let's do the same thing. We're going to deal with another quadratic here. Square both sides. We get 4v plus 45 equals... I'm getting pen pain. V squared plus 12v plus 36. Set everything equal to 0 here again. We'll get v squared plus 8v minus 45. Minus 9 equals 0, right? Yeah. So that factors into v plus 9 times v minus 1 equals 0. So v equals negative 9 and v equals 1. Let's take a look and see if that works. Negative 9 times 4 is negative 36, plus 45 is 9. Square root of that is 3. Negative 9 plus 6 is negative 3. Negative 9 does not work. That is extraneous. Extraneous. 1. 4 plus 45 is 49. Square root of that is 7. 1 plus 6 is 7. That checks out. V equals 1 works. All right, let's do it again. I can do it again, too. See? Square both sides right here. I'm going to get 5b minus 29 equals b squared minus 10b plus 25. Set everything equal to 0. A lot of factoring practice here. B squared minus 15b 29 plus 54 equals 0. That factors into b minus 6 times b minus 9 equals 0. So b equals 6 or b equals 9, or both or neither. 30 minus 29 is 1, square root of that, and 6 minus 5 is 1. That works. 9. 45 minus 29 is 16. Square root of that is 4. 9 minus 5 is 4. Both work. Neither extraneous. We're good to go. Let's do it again. Radical's isolated. If the radical's not isolated, it's a way different story. We got to isolate it at all costs if we can. This will be b squared minus 10b plus 25, like last time, equals 7 minus b. Add b over, that's 9b. Subtract 7 over, that's 18. Factor that, that's b minus 6 times b minus 3 equals 0. So b equals 6 and b equals 3. Let's try it out. 6 minus 5 is 1. 7 minus 6 is 1. Square root of that is 1. That works. 3 minus 5 is negative 2. 7 minus 3 is 4. Square root of that is 2. Negative 2 does not equal 2. That is extraneous. And b equals 6 is all we can do. All right, these next two problems, the way I'm seeing it right now, I'm going to need more room. Now, they won't be able to stay on the screen when I'm done, but I'll deal with them as I do. Now, these can be treated the same as square roots, right? The 1/2 power is square root. So that is square root of 3x plus 7 equals 5 plus the square root of 6 minus x. Now, I cannot fully isolate both radicals, but I can isolate at least one of them, and that's as good as I can get for now, and I'm going to deal with that. When I square both sides here, it'll cancel out the radical on the left, but it will not fully cancel out the radical on the right. I get 3x plus 7 here, and this is a perfect square trinomial. It's a squared plus 2 times ab. 5 times root 6 minus x is 10 root 6 minus x, plus b squared. Square root of 6 minus x squared is indeed 6 minus x, but that radical is still there. Let's keep working that out. 25 plus 6 is 31. I have that minus x and plus 10 root 6 minus x. Let's get this by itself as much as possible. If the 10 stays, that's fine. But these I got to move over. Add x over, you get 4x. Subtract 31, you get negative 24, I think, equals 10 root 6 minus x. Now I could, not divide by 10. I could, but I could reduce these. Let's divide everything by 2. Just make it a little bit smaller. 2x minus 12 equals 5 root 6 minus x. A lot of people won't maybe do something like that, but I will. Before I square it, I want to try and make the numbers a little bit smaller. In fact, if I factored out a 2 from there, these are small things I'm doing that many probably wouldn't, but it's kind of nice when I square it so I'm not dealing with the pain of bigger numbers. You know, I'm not going to factor out the 2. People are going to wonder what I'm doing when I square it. So let's square both sides right now the way that it is. And we'll have, keep purple, 4x squared minus 48x, that's minus 2ab, plus b squared 144 equals 25 times 6 minus x. Whoa, this is going to be pretty big. 4x squared minus 48x plus 144 equals 150 minus 25x. That's 4x squared. Told you I need the room. Minus 23x minus 6 equals 0. I sure hope that factors. Let's try it. 4x and x. Yeah, this does. Minus, I just had it in my head. Minus 6 and plus 1. Negative 24 plus 1 is negative 23. That works. So either x equals negative 1/4, subtract 1 divided by 4, or x equals 6. I gotta try these. I'm gonna start with 6. All right. These are square roots, remember. Let's look at this one. Yeah, this is fine. 18 plus 7 is 25. Square root of that is 5. 6 minus 6 is 0. Square root of that is 0 plus 5 is 5. So 6 checks out. Negative 1/4, I'm not as much a fan of checking out here. I don't know if this is going to... Negative 3/4 plus 7 is 6 1/4. Negative 3/4 plus 7 is... Oh, it's 25/4. Actually, that does work. Square root of that. Square root of 25/4 is 5 halves. 5 plus 6 minus 1/4. So 5 plus 25. 20 square root of 25/4. So square root of 25/4 is 5 halves in itself, and that's 5 plus 5 halves. Did I do that right? 6 minus negative 1/4 is 25/4. That's 5 halves in and of itself. 5 plus that. Doesn't look like that one works. I just don't know if that was my right math. I'm going to deem that extraneous. I might have done something wrong when I said that, but I think that didn't work. I think here I had 5 plus 5 halves, and here I think I just had 5 halves. So yeah, I don't think that one works. I think that one's extraneous. I assumed it was. Sometimes those negative fractions don't always pan out. Never really seen them pan out, so maybe not. Sorry if it did work. I'm just trying that one in my head. All right, this one's the same kind of problem here. Kind of a lot to do. Square root of 3x plus 4 there, and square root of 7x minus 3. Now I already have one of these isolated, so I'm going to go ahead and square right now. You do not want them together on the same side of the equation. That's going to deal with worse radicals that are not in your favor. Although I still do have radical issues here. So 1 plus 2 root 3x plus 4. This is my perfect square trinomial. Plus 3x plus 4, and this is 7x minus 3. A squared plus 2ab plus b squared. 3x plus 4 plus 1 is 3x plus 5 equals 7x minus 3. Okay, subtract 3x over, subtract 5 over. This time I can actually divide this 2, which is nice. Like, boom. And I'll have square root of 3x plus 4 equals 2x minus 4. Now when I square both sides again, I'm going to have 3x plus 4 equals 2x squared is 4x squared minus this is 16x plus 16. Subtract the 3x over, subtract the 4 over. You'll get minus 19x, and subtract the 4 over is plus 12. Let's check that out. 4x and x. I'm going to imagine the one that's a fraction is extraneous. I don't know if that's true. Minus, minus. Let's hope it factors. Yeah, 4 and 3. Negative 16 minus 3. So x either equals 3/4 or x equals 4. Let's try 4 first. 1 plus 12 plus 16, square root of that. 1 plus 4 is 5. 28 minus 3 is 25, square root of that is 5. That checks out. What's our other number? 3/4. 9/4 plus 4 is 25/4. Square root of that is 5/2. 1 plus 5/2 is 7/2. So 7/2 equals 3/4. 3/4 times 7 is 21/4. Minus 3 is minus 9. Excuse me, minus 12/4. Wait, what was it? Hold on. 21/4 minus 12/4 is 9/4. That's 3/2. Square root of that is 3/2. That does not work. So that one does not work there. Whoops. That one is extraneous. No or, just 4. Okay. So there's x equals 6, x equals 4. I'm going to cut out all this stuff and I'm just going to write those answers. X equals 6, x equals 4. With those extraneous ones in the way. Out of the way. All right, solve each equation. These are kind of similar. I'm not going to convert them to their radical forms. There's rational exponent form. We want to isolate that portion before we raise them to their reciprocal powers. Remember, this 1/2 we squared. That's times just to the 2 first power. So this one I'm going to raise to the 2/3 power like that. But I can't do it until it's fully isolated. So I'm going to start by subtracting 8. I get 375 equals 3 plus times v plus 12 to 3/2. Then you divide by 3 and you get 125 equals v plus 12 to the 3/2. Okay, now if I raise both sides to the 2/3 power, what's going to happen is on the right side, I'm just going to have v plus 12, which is cool. Or I'm going to put it on the left side now, v plus 12. On this other side, by the way, no extraneous solutions. That's not going to be a concern. Here's the cube root of 125 squared. Cube root of 125 is 5. 5 squared is 25. So subtract 12, you get v equals 13. For time's sake, I'm going to move forward. Number 116, I'm going to subtract 6, then divide by 5, then cube it. This is a cube root, so I'm going to then cube it and then keep solving. Subtract 6, I get 20. Divide by 5, I get 4. You follow? To the 1/3 or cube root of. As long as it's a 1/3, I'm fine putting cube root, something like that. I like that. Whenever it's like the squared and that kind of stuff, not as much. But like that, that's fine. And that was 4. Remember, subtract 6, divide by 5. So let's cube both sides. Cube both sides there. I get 3x minus 26 equals 64. If I add 26 over, I get 3x equals 90. Divided by 3, I get x equals 30. Like that. Whew, okay, divide by -2. I get 13 minus 3p to the 3/2 equals positive 1,000. Now we will raise these to the 2/3 power, which is taking the cube root and squaring it. So 13 minus 3p on the left side. Cube root of 1,000 is 10. 10 squared is 100. Let's subtract 13 and divide by 3. Is that? I guess it's just that. 113 over 3. Let me make sure I didn't subtract divide by -3. 113, yeah. I think that's it. I guess it's a fraction. Okay, -1/2 power. I'm going to make the -1/2 power positive first. So let's just raise the negative first just to begin with. That way, 1/5 the negative first is 5. Now I have a plus 29 to the 1/2 power, which is also square root of, right? I like putting those whenever it's just that. So let's square both sides right there. And that's a plus 29 equals 25. Subtract that, you get -20. I'm not subtracting right. -4. -4. And it's not extraneous, by the way. That should work out. Okay. Identify the domain and range of each, then sketch the graph. Well, first I'd like to kind of write this in its graphing form, at least in my head, how I see graphing form right there. My A is -1, my H is -4, my K is 1. By the way, they're asking for domain and range. This is a cube root graph. It'll be all real numbers and all real numbers for these guys right here. They go forever, left, right, and up, down. My HK is -4, 1. I'm going to start over here. We did one cube root earlier when we did inverses. My A is -1. It'll take my 1, 1, 8, 2 concept and flip it over to 1, down 1, and over 8, down 2. Left 1, up 1, and left 8, up 2, which I can't really fit. I'll pretend like I can, in a way, in terms of graphing that cube root right there. Not perfectly plotting through, but I'm trying. And there's my cube root graph. Okay, let's go. Y equals -1/2 times cube root of x minus 3 plus 5. Again, domain and range are all real numbers for cube roots. Our center is at 3, 5. And 1, 1, 8, 2 is going to be flipped over from the negative and halved. Instead of 1, 1, it's 1, 1/2. Instead of 8, 2, 6, 7, 8, it's going to be 8, 1, down. 1, 1/2, and 8, 1. Like that. A lot skinnier. Or a lot wider? Shorter? Vertically compressed is the proper terminology for that. Okay, very, very skinny. You know what? It goes up and down forever, right? This isn't flattening out. Range is all real numbers. It goes up and down forever. It just goes left and right a lot faster than it goes up and down. All right, a couple square root graphs here. Domain and range is limited this time. I'm going to actually graph it first, and then I'm going to talk about what that domain range is. Now, the vertex is at -1, -1. It's actually not a vertex, but it's that center point, my HK. -1, -1 is where I'm going to start this thing right here. And this -1/2 is going to do the same thing. First of all, square root graph only is sideways, half parabola sideways, but it's going to flip over, and it's going to be vertically compressed by a factor of 1/2. Square root of 1 is 1, take half of that. Square root of 4 is 2, take half of that. Square root of 9 is 3, take half of that, like this. Now, as you can tell, because it's only a half parabola, it does not go forever left, and it does not go any higher up than this. It has a limited domain and range. The domain is actually x is greater than or equal to -1. The range is y is less than or equal to -1. Now, these have to do with these guys right here, our HK values. Your domain is specifically limited to the fact that we can't take square roots of negatives. Your domain tells you that x plus 1, the thing inside, has to be greater than or equal to 0. If you subtract 1 from both sides, you'll see that x is greater than or equal to -1, and that's where we go from there. The range is limited kind of by k. K is the highest or lowest value you can be, because -1 is like that vertex-ish point, and it goes downward. That's the highest we can be. Y is less than or equal to that k in this case. All right, number 122. I can predict domain and range based off what this is. X should be greater than or equal to h, or x minus 3 is greater than or equal to 0. X is greater than or equal to 3. We'll go to the right from 3. By the way, if I rewrote this, please, y equals 4 root x minus 3 minus 1. Your k, -1 is the lowest it gets, and it goes up from there. Positive means it goes up. Range is y is greater than or equal to -1. You'll see that on the graph, though. We're going to start at 3, -1. Let's start at 3, -1 right there. This 4 is our vertical stretch. Over 1, square root of 1 is 1, times 4 is up 4. Over 4, 2, 3, 4, up 2 times 4 is up 8. And that's kind of all I can fit there. It's only a half parabola and a sideways one at that. And it goes like that, and that seems to fit our domain and range that we mentioned. Seem to be the only ones that they show there. Now we're graphing some rationals. The rest may be rationals. Everything else the rest of the way is rationals. This is kind of a unit 3, if you will. Those were all radicals, I think. I think we were all in radicals there. All right, these are our basic rationals right here. These are our a over x minus h plus k. As long as we're in that form, I'm going to kind of keep talking about it like that. I'm not going to dive into the more complicated version of find this, find that. So let's stick to that. So here, this is that -1. I'm going to treat that as a -1 up top, like that. So my a is -1, my h is -1, and my k is 0, right? Plus 0 there. So we have a vertical asymptote at x equals -1, a horizontal asymptote at y equals 0, and I'm going to go ahead and graph those two right now. How long has this been so far? 3 hours. All right. So x equals -1, y equals 0. Whew. -1 stretch factor. So -1 divided -1 divided by 1 is -1. -1 divided by 2 is -1/2, etc. A third, a quarter. I don't really like them too much when they're ones because all you have are fractions the rest of the way. Basically, it skinnies up in that direction. A half, a third up, a quarter up, like that. And it kind of works that way. Most teachers probably just say, just figure out which direction they go. But because it's negative, it flips upside down like that right there. The biggest point I have, I didn't make it go through. And there's our graph for that first one. This next one here, the a looks like it's -3. The h is -1 again. The k is -1. So your vertical is at x equals -1. Your horizontal is at y equals -1. So let's go ahead and graph those. Y equals -1. X equals -1. -3. I don't know if you can see it. I don't know if my picture's in the way. I'm not really looking at it. -3 divided by 1 is -3. -3 divided by 2 is -3 halves. -3 divided by 3 is -1. -3 divided by 6 is -1/2. -3 divided by 1/2 is -6. I like those points there. -3 divided by -1 is +3, and 1.5, and then +1. 4, 5, 6 is half away here. A lot of teachers don't require these points here. I like to get a lot of picky points to just show as precise as I can get, because these are the actual y values for these x's without using a table, which is kind of sweet. And I won't use those for the more complicated graphs, which we may be running into right now. I don't know. Let's see. Yes, we are. Identify the holes, vertical asymptotes, x-intercepts, and horizontal asymptotes of each, then sketch the graph. I'll go in the order I prefer. What I like to do here is factor this thing first, GCF of x on top, and then a 4 on bottom, because if there are any holes, I like to find them. It doesn't look like there are. So I'm going to kind of have it like that there. Holes, none. A hole appears if I can cancel a factor on top and bottom, which I could not. I don't like graphing first and simplifying them later. I like teaching the simplifying first in domain restrictions, but I've taught it once before, so we're there. Vertical asymptotes are next. Anything that didn't cancel that is still a restriction in the denominator is going to be something to talk about. X can't equal 2. 2 is the restriction in my domain. Therefore, x equals 2 is the equation of the vertical asymptote. That is the line, the dotted line, which we'll see it on. There's that. This doesn't have a horizontal asymptote because the degree of the numerator is larger than the degree of the denominator. This has a slant asymptote, and I can find the equation of the slant asymptote by doing long division on this thing here. I have to do x squared plus 2x. I don't like that it's starting off with this problem. That's okay. Over 4x minus 8. 4x goes into x squared. Check this out. 1/4 x times 4x times 1/4 x is x squared. -8 times 1/4 x is -2x. And no, these do not cancel. That is actually 4x right there. 4x goes into 4x one time. 4x times 1 is 4x. -8 times 1 is -8. 0 minus -8 is 8. That's my remainder. So this function can also be written as f of x equals 1/4 x plus 1 plus 8 all over 4x minus 8, which I can also reduce that part. F of x equals 1/4 x plus 1 plus 2 over x minus 2, if I divide those all by 4. Now this represents your horizontal or slant asymptote. In this case, it's a slant asymptote. Y equals 1/4 x plus 1. Y equals 1/4 x plus 1. I'm actually going to graph that. The remainder can help me determine how far above and below the asymptote I am at any point. I know I don't cross the asymptote at all because my numerator can never be 0. Unfortunately, what I'm telling you right now are things you would have had to learn at some point. Guys, I'm already 3+ hours in. I'm not going to be slowing down everything. I'm just showing you what you have to do to graph this. This is actually what you have to do to graph it. X-intercepts and Y-intercepts. Let's go to those next. X-intercepts is when the numerator is 0. When does x times x plus 2 equal 0? At x equals 0, right? 0. And when x is negative 2. The y-intercept, well, I already know it's 0 because the x-intercept is 0, but that happens by substituting 0 for x into this. F of 0 is 0 over negative 8, which is 0. So your x-intercepts are those two, your y-intercept is that. And this is the information we need to graph, with also the knowledge that because the remainder can't ever possibly be 0, we'll never cross the slant asymptote. So let's go ahead and graph this thing with the vertical asymptote at x equals 2. The slant asymptote being y equals 1/4 x plus 1. That starts at 1. It's rise 1, run 4. Rise 1, run 4 like that. Fall 1, run 4 to the left like this. So I'm going to draw a line that goes like that. That's your slant. Your we have 0, 0. And negative 2, 0, and it never crosses the x-axis again. So we know that this stays underneath the slant right here, crosses through these points, and curves back down. Let me try that again. Goes up above and down below there, and crosses through like that. And this thing never hits the x-axis down here. That means it must be above right here. It goes up and through like that, and that is your graph. I'm not saying it was easy or like that's it or whatever I'm saying, but that is the complete answer. I have no more to find. All right, number 126, also a slant asymptote, I just noticed. So you're going to deal with slant asymptotes here. What I like, I don't really, what I like is they say, hey, tell about the horizontal asymptote. They don't have horizontal asymptotes. They have slant asymptotes. I know they have a slant because the numerator is larger than the denominator, which means we are going to have to do long division on this thing to figure out what the slant asymptote equation is. Let's start by factoring this here. A GCF of x, and I get x squared minus 9 over a GCF of negative 4, and I have x squared minus 4. Both of these are differences of two squares here. And I get x times x minus 3 times x plus 3. At least that'll be fun. Over negative 4 times x minus 2 times x plus 2. When I say fun, I mean, well, you get, well, this will be fun. So there's a factored form of this. Nothing canceled, so no holes. Let me put this other one up and out of here. So holes, none. Nothing canceled. These are the only two ones we're graphing. Sorry, I didn't make the final thing. There's no problem with these being the only ones, but these were both slants. We didn't get any horizontals. I have some other videos where we do horizontals, but you get to play with slants, which is kind of nice. Vertical asymptotes are x equals 2 and x equals negative 2. The two things that they're not allowed to be are where the asymptotes are. And don't put plus or minus 2. These are two different equations of lines. No horizontal. It's slant asymptote right here. Numerator is larger than denominator. So let's do long division on that thing and figure out what that is. X cubed minus 9x all over negative 4x squared plus 16. Negative 4x squared goes into x cubed negative 1/4 x times, and that will give us x cubed, that's an x, negative 4x there, and that's negative 5x, and negative 4x squared can't go into that. So that's actually all we have to do in long division. So this is as a function. It's now written as negative 1/4 x minus 5x all over negative 4x squared plus 16. And I get if you're having trouble with a lot of the stuff going, wait, what? Especially on the division. This is your slant asymptote right here. It's y equals negative 1/4 x, like plus 0. So mx plus b is just the slope. Doesn't show a y-intercept there. And then right here, you know, I could write this better, given that that had a factor of negative 4 times x plus 2 times x minus 2. I suppose. Let's give just a better rewrite of that. Let's factor out that bottom. If I factor the negative 4 out, then a negative times a negative is a positive. So I have negative 1/4 x plus 5x over 4x minus 2 times x plus 2. I don't know if I'm going to have to do anything with that because I know where it's going to be crossing that asymptote in a second. We'll talk about those in a bit. Intercepts here. We have 3 of them. 0, 0, 3, 0, and negative 3, 0. That's when the numerator is 0. The y-intercept is when x is 0. Solve for y, and that will be 0, 0, because, again, the x-intercept right there. And I can find out where we cross the asymptote, the slant asymptote. It will cross at 0, 0 right here, because when 5x equals 0, x equals 0, this is where we cross asymptote. Let's see if we can figure everything else about this that we need based on that information alone. Maybe, maybe not. The problem is it crosses where the x-intercept is. So we might have to do a sign chart given the remainder test and see when we're above and below the asymptote with that. We'll see. Very confusing, but let's do it. And don't get me, and everything you see is everything I'd have to do with this problem. I'm speaking slowly on it, but this is everything I'd have to do as well. So x equals 2. X equals negative 2. And my students have a multiple choice final, but would they know how to select which one we do as an answer? Negative 1/4 x plus 0. So down 1, right 4. Down 1, right 4. Up 1, left 4 right here. And there's our slant. Now you can cross. It's possible to cross slant asymptotes. Like I said, we're going to cross this. 0, 0. 3, 0. Negative 3, 0. Now, I guess we already knew we were going to cross it. We didn't know which way it was going to go, though. The only thing I know for sure is that's the only place that it does cross. So this for sure goes that way. This for sure goes this way. The question now is, what happens here? Does this part, I'm just going to show in green, does this do this? Does it do this? Does it do this, which is my guess, or does it do this? How do we find out? You do tests of values. Now you could, it's not too extreme here, but like if I plugged 1 into my equation, I could see if the thing is positive or negative. But I don't want to test in the original, because testing in the original means if it's negative, it might be negative, but above, right there. I guess it couldn't technically be, because then I have to cross the x-axis again, so it's but I want to test with the remainder. I want to see when is the remainder positive or negative. When it's positive is when we're above the slant asymptote, and when it's negative is when we're below the slant asymptote. So I'm going to try and plug in 1 and negative 1, and I want to see the signs of those in the remainder. When I plug in 1 into here, I get 5, which is positive, over 4 times negative 1, which is negative, times positive. Positive over positive times positive is negative. I plug in 1, I get a negative value. I don't know what it is, but it's negative. I plug in negative 1, I get a negative divided by positive times positive. Negative divided by negative, that's positive. So I will be above and below. So the graph will do that. I'll be here and here. You can try and plug in actual values there, but the remainder is a good test, especially if your slant is very extreme and if it doesn't cross right there. But that is what your graph looks like. Okay, and that's it for those ones. Simplify each and state the excluded values. This is where we have restrictions in our domain we have to take care of. This is where we get to play with more quadratic factoring, which is cool. So on the top, let's see. I assume these can factor, otherwise it's just no fun. Negative 4, negative 2, or negative 4, positive 2, negative 2, plus 4. Negative 6 plus 4 is 2, excuse me, plus 2 minus 4, plus 2 minus 4. There we go. And if I factor out a 10, here I get p squared plus 4p plus 4. That is 10 times p plus 2 quantity squared. P plus 2 over, one of those p plus 2s is that. So I'm left with this, 3p minus 4 over 10 times p plus 2. We'll leave it like that. They're simplified. Restrictions, p cannot equal negative 2. Now, there was this multiplicity of 2, but there's no such multiplicities when it comes to excluded values. You just say what it can or can't be, or you say what it can't be. Okay, I got a GCF on top of 2. And I have n squared plus 2n minus 3. And on bottom I have a GCF of 8. And I have n squared plus n minus 2. 2 over 8 is 1/4. And now I can factor that into n plus 3 times n minus 1 over n plus 2 times n minus 1. And there's that 1/4, so a 4 down there. And that's it. Oh, wait, n minus 1's cancel. And I have n plus 3 over 4 times n plus 2. Okay. Now, n cannot equal -2 or 1. Now, at 1, you would have actually had a hole. Like if this was a function to graph, at 1, you would have had a hole. And you would have had to plug in a number into that x, or n in this case, to see what the y value was in this simplified thing to figure out what the y value of the hole was, where it approaches. -2 is a vertical asymptote of sorts, but n can't be either. It doesn't matter if it cancels. Canceling means dividing something by itself, and you cannot divide 0 by 0. Okay. Nothing to do on top on this one right here, just 56x squared, at least not yet. On bottom, you can factor out a 40x, and you have x plus 1. Now I can do some stuff. X squared divided by x is x. 56 over 40, I can divide 8, and I get 7 over 5. And there's the reduced one right here. X cannot equal 0 because of the 1 I canceled out there, and x cannot equal -1 because of the thing that remains there. Those restrictions. Interesting problems as far as these. We generally multiply them first before doing this. All right, 63x, nothing I can do there. On bottom here, I have a 9x that can factor, and that's 2x minus 1. X over x is 1. 63 over 9 is 7, so I have 7 over 2x minus 1, which is simplified. X cannot equal the 0 from the whole, and also plus 1 divided by 2, x cannot equal 1/2. Okay, now we are going to divide and multiply. Now, division is multiplying by a reciprocal. So you see this 1 over x plus 7 right here. I can flip it over and become x plus 7 over 1 when I multiply. And on top right here, I can factor a 7x out, and I get 7x plus 4. And in this denominator here, I have a 7x times x here. I imagine this is 4 and 4. I imagine something's going to cancel. I'm not certain. I'm going to try that. 28. Yeah, plus 4 is 32. And x plus 7 over 1. Okay, anything here is dividing anything there. So if I could cancel, I would. I can't, but these can cancel right here. Boom, boom. Cancel means becomes 1 when they divide because they're products, they're factors. So on top, I still have 7x times x plus 7. And on bottom, I have x plus 4. That's kind of all I can do. So there's my reduction. Now, x is not allowed to equal the following. -4. Subtract 4 divided by 7. -4 sevenths. And -7. Now, the -7 comes from this. That is something that was in the denominator at one time. I know we flipped it later. I know it didn't cancel. I know this thing's up here. X is allowed to equal 0. That's totally fine. It cannot equal -7. It was in the denominator at one time. Because it was, that would be dividing by 0. We can't do that. All right, number 132. 2 divided by 2 is 1. I'm going to take care of that right now. 6r squared is on top. On bottom, I can factor out an 8r squared, and I'm left with r minus 7. R squared over r squared is 1. 6 over 8 is 3/4. And we'll have 3 over 4 times r minus 7, the quantity r minus 7. R is not allowed to equal 7. Those r squareds would have represented as 0. And I think that's it. R can't equal 7 or 0. All right, some more multiplication. Got 1/2 there. 24x minus 56. Let's try and reduce some of that. That's 1 times 20. That is that. 8. Is 8 the largest? Let's try that. 3x minus 7. Yep. over, there's the 3x minus 7. 2 times 3x minus 7. 3x minus 7 3x minus 7 is 1. 8 over 2 is 4. So we're left with 4. You know what, though? X still can't equal, add 7 divided by 3, 7/3. And you're probably sitting there going, wondering, where am I going to plug x into here? You're not. You're going to plug x into here, or 7/3. You're going to plug 7/3 into here. They're just saying these two things are equivalent. Just don't plug 7/3 into there, otherwise you get 0 over 0. Right? So there's still a restriction. There's still a problem for wholes. That's the big part. Okay, dividing is multiplying by the reciprocal here, so let's go and flip the second guy. That's 1 over 9x times, and we can factor a 2x squared out on that, when this flips. Factor a 2x squared out, and I have x minus 5. And then on bottom, I have that 2x squared that was there. Those divide to become 1, and I have x minus 5 all over 9x. Now, x cannot equal 0 from that x. It's not a 9 or negative 9 or anything like that. It's just 9 times 0. And then 0 from this as well, although those are gone and dealt with. And the x minus 5 was at one point, this was at one point in the denominator, right? I didn't write it factored, but it was down there. So x cannot equal 5 as well. That's another restriction. All right, simplified expression. This is addition and subtraction of these things. What we need is a common denominator, and then we multiply, we add or subtract the top as quantities. This is that minus that kind of thing. This is a common denominator here, so I have 5n minus 6 minus 5 all over this, and it's worth factoring this for a couple reasons. 1, to achieve a common denominator if you don't have it, which we do. 2, to find our restrictions, because we still got to find those. And 3, if anything can factor on bottom with on top, then we can end up, on bottom, then we can, if there's a common factor on top and bottom, then we can divide and cancel them and actually simplify it more. So I'm going to attempt to do that. Maybe it can't factor. I do not know. Let's find out. 3 and 5. No. 15 and 1. Oh, maybe it can't factor. 5 and 3. 5 and 3. 5 and 3. Negative 25 minus 3. Yes, it can. Okay, so that's 5n minus 11 over 5n minus 3 times n minus 5. So here's the deal. We're done. But let's say this did say 5n minus 3, right? Then that would cancel with the 5n minus 3 on that, and we'd have 1 over n minus 5. That's not the case. But we still factored to check it out. Now, there are still restrictions. N cannot equal, add 3 divided by 5, 3/5, and n can't equal 5. That's why we still factored. It still had benefit, even though we have a common denominator. Same thing with this problem here. Now, this is 6 plus a minus 6. 6 plus a minus 6 all over a minus 3 times a plus 2. A. 6 minus 6 is 0. We're left with a on top. So a over a minus 3 times a plus 2. Nothing factors, cancels, whatever. I can't imagine. I assume these are procedurally generated. So I can't imagine that these, oh, my camera's tilting a lot. I had no idea. Sorry. Am I still here? All right. I can't imagine that these procedurally generated ones will actually cancel something on top and bottom, but that's okay. A cannot equal 3 or negative 2 here. It can equal 0. We can divide from 0, not by 0. These do not have a common denominator. Let me rewrite these again to give myself a little more space. These do not have a common denominator, but you want to find what's missing in the other guy here. This don't have no x minus 9, and this don't have no x minus 7. Now, in getting a common denominator, we now have the same thing on bottom, so that's good. So this all on bottom is x minus 7 times x minus 9, just one instance of each. We got to distribute 5 into the x minus 7s to get 5x minus 35, and distribute 7x into x minus 9 to get 7x squared minus 63x. Now on top, we'll try and combine like terms and all that. 7x squared minus 58x minus 35 over this. Now, this is one of those cases where, again, because it's procedurally generated, I have no guarantee or thought to the notion that this will factor. I don't know. When I make a problem, I try to make sure that it does. They're not easy to make. Let's try and see if it can, because if it can and something can simplify, you got to attack that. 35, I'm really going to just look at like 5 times 7 there to get to 58. 7 is 49. No, I don't think that factors. So we're good right there. That's all we got, and it can't go any further. We're done. We're done right there. X can't equal 7 or 9. Sorry about that. X can't equal 7 or 9. And I really ran into this other problem, so I'm going to move these things over here. Give me 1 sec. All right, let's do. Okay, like that. Perfect. Okay. Last one of this set. Multiply top and bottom by p minus 7. And multiply top and bottom here by p plus 6. All right, 5 will distribute into these. P plus 7 times p minus 7. That's the difference of 2 squares. And then on bottom here, we have p plus 6 times p minus 7. Don't distribute the bottom, right? The bottom's fine factor. There's nothing we can do with it. Our point at the top is to combine these top 2 parts that weren't combined before into something. So 5p plus 30 through that distribution. And this is p squared minus 49. So this becomes p squared plus 5p minus 19, which is very unfactorable. I can just tell. P can't equal negative 6 or 7. Yeah, I really like the ones that can. Sorry that those can't. Solve each equation. Remember to check for extraneous solutions. So here we do need to get common denominators, and when I do, I can multiply all sides by that thing, and then we're all good to go. I know teachers do these differently. The end result's still the same. I want to factor this into m times m plus 8. So now you can tell what's missing in all these things here. Let's rewrite it to give ourselves some space. 1 over m times m plus 8 plus m minus 5 over m equals m minus 3 over m plus 8. Okay, got to see what's missing in these other quantities here. This is missing an m plus 8, so we're going to multiply that on top and bottom. This is missing an m, so we're going to multiply that on top and bottom. And this has it all, so we're good there. So now that we have a whole denominator that's the same, these are equations. These are equations, not expressions. These are different from all the problems we did before. Notice how everything here was still a fraction. Everything, except for that 4. Everything here was still a fraction. Right here, my goal is to find out what value of m makes the numerator true, just like the x-intercepts and those graphing rational function things. I want to find out what makes them true in the top. The bottom, I couldn't care less about what the bottom does, except I just don't want to divide by 0. But the bottom has nothing to do with solving things on the top. I could multiply both sides right now by m times m plus 8. M plus 8 times m. And that would cancel out everything in the denominator. And I'd only have numerators out. But my goal was getting a common denominator so I could do that. And everything on the top compares properly. So I'm basically getting rid of that. I'm multiplying both sides by m times m plus 8. Or m squared plus 8m. And it's canceling the denominator in doing so. I still have to note the extraneous solutions. If they exist, m should not be able to equal 0 or negative 8. I'll take note of that. But this only applies in equations because I can multiply both sides of the equation by it. And I'm stressing this to my students who suck at this, who always start canceling these things out. Not at this. They start canceling this stuff for no reason. You can't cancel that. That's an expression. You can't do that. You can do that in an equation. And I'm sorry for spending a long time on this, but frustrated over when I see it. I am. I don't want to see it anymore. All right, so what's on top? 1 plus foiling. M squared minus 5m plus 8m is m squared plus 3m minus 40 equals, and this is m squared minus 3m. Now the m squareds can subtract and go away. I can, let's keep working this out. 1 minus 40 is negative 39, so 3m minus 39 equals negative 3m. Add 3m, add 39. You get 6m equals 39, and you get m equals 39 over 6, which is 13 over 2. If I did that right, m squared plus 3m minus 41 plus that. Yeah, I think so. M is 13 over 2. These restrictions have no bearing on that. Whatever, just 13 over 2. You don't state restrictions after that. No, if this is one of your restrictions, then it's extraneous. That's all. Okay, these two are the same right here, but we still got to factor them to figure out what the r minus 1 is potentially missing there. Now, if this was factorable, which actually it is, don't factor it unless it can cancel something out on top and bottom and works out in our favor of common denominators. I don't think it can. Leave this as it is. R squared plus 13r plus 36. Because we got to combine this with things on this side. We're not factoring yet on that. We are factoring the denominator to look for a common denominator. This is r plus 10 times r minus 1. So now we see what's missing in this r minus 1 bit. 1 over r plus 10 minus 1. So both of these have those. This is missing in r plus 10. Now the denominator is obsolete for our sake, except the fact that r can't equal 1 or negative 10. So now, bye-bye, given that I'm going to distribute that. So now we have an equation that says r squared plus 13r plus 36 equals r squared plus 10r plus 1. Subtract the r squareds, subtract 10r, subtract 36, and r equals negative 35 over 3. Makes me feel better about the previous answer that I once again have a fraction. Either I'm doing everything wrong, or I probably did both of those correctly. Now, the restrictions were negative 10 and 1. That is neither negative 10 nor 1, so that is good. It is not an extraneous solution. We're good. All right, let's keep moving forward, and I have a lot more room down here to work. Here I have r minus 9 over, this is r times r minus 4 plus 2 over r squared times r minus 4 equals 1 over r minus 4. So it looks like this guy's missing an extra a. This guy's got it all, and this thing's missing a whole r squared, a whole kit and caboodle. All right, as we attempt to distribute that guy right there, and 1 times r squared is r squared, the bottom is all good. R can't equal 0 or 4. Let's remember those. We're going to have r squared minus 9r plus 2 equals r squared. The r squareds cancel again. That's no fun. I'm looking for quadratics. Add 9r to both sides and divide both sides by 9. R equals 2/9, like that. Not a restriction issue. Once again, fine solution. And this is the last problem. The last problem of everything here. Let's go ahead and let's do it. I didn't realize we're at the last problem. Here we go. I'm excited suddenly. P plus 1 over 2p squared. Not every problem of every type was covered. Even with 142 problems, we didn't hit every problem we could under the sun. You know what I mean? But I think we hit a lot, especially in that first unit. I can factor a 4p squared out, and here I have p plus 7. Here I can factor, it's the same thing. 4p squared, p plus 7. Okay, this is kind of interesting. This is missing a 2, right? 2 times 2p squared would be 4p squared. So it's missing a 2, and it's missing the p plus 7. So it's missing both this and that and all that jazz. So now that bottom is, remember, p can't equal 0 or negative 7, in case that pops up. And this is a quadratic. In the end, this will be a quadratic. So let's do it. Oh, you know what? This would have been a common, that's okay. All right, I got 2 times, FOIL that's p squared plus 8p plus 7 equals 1 plus p plus 6 is p plus 7. Distribute that. I have 2p squared plus 16p plus 14 equals p plus 7. Set it all equal to 0. 2p squared plus 15p plus 7 equals 0. This factors into 2p plus 1 times p plus 7. 14 plus 1 is 15. So p equals negative 1/2, or p equals negative 7. Now, we mentioned that negative 7 was not allowed. That would have you divide by 0. Negative 1/2 is fine. Negative 7 is not. That is extraneous. And negative 1/2 is there. Good, I'm glad we hit one of those. Back to a quadratic again as well, in case people are confused on what to do. Okay, and this blank page says that that is it. 142 problems tackled in about 3.5 hours there. not too bad. All right, guys, that ought to do it for this one. Now, I do plan on making timestamps for these in case I haven't done them yet. You're going to have to give me some time on that to actually make that happen and sort these out in a certain way. And, apologies for slowing down on some parts where maybe I didn't have to, like the very beginning, solving things like that. And apologies for not hitting every single kind of problem. We only had slant asymptotes, none of the horizontals. I linked, hopefully down below here, the other final review video, if that kind of covers some things that we did from last year, at least problem types, or more condensed versions of them, or I explained them a little more thoroughly because there were less problems, but I did it in still about 3 hours. So that'll do it for this one, guys. This is Mr. Robinson. Thank you so much for watching, and take care. I will see you in the next one.